Namaste and a warm welcome to all. I am Himitri Trivedi, a PhD research student at Saurashtra University, extend my heartfelt greetings as we gather for day 8 of our Vigyan Yatra, a travel for scientific Indian minds towards Vikshit Bharat. In the words of our ancient wisdom, Vijnanam Silataya Yuktam Vicharan Chadhimata तत्वज्ञानात परम विज्ञानम सर्वज्ञानम सुखावहम अर्थात science when combined with character thought and intelligence and rooted in the knowledge of principles is the supreme science bringing happiness and encompassing all knowledge. Today, we continue our journey towards a developed India driven by science and innovation. This series of conferences, jointly organized by Department of Physics, Saurashtra University, Rajkot, Vigyan Gurjari, Gujarat Prant Unit of Vigyan Bharati, VIBHA, and GUJCOST, Department of Science and Technology, DST, Government of Gujarat under Gujarat Vigyan Sammelan, GVS 2024, is a celebration of our commitment to scientific excellence and progress. Today, we are privileged to have respected speakers Dr. Balasubramanian sir, Scientific Officer at Facilitation Center for Industrial Plasma Technology, FCIPT, Institute for Plasma Research, Gandhinagar, and Dr. Vipul Kher sir, Associate Professor, Department of Physics, Sardar Vallabhbhai National Institute of Technology, SVNIT, Surat will share their expertise on fascinating topics. So, let's embark on this journey together, united by our passion for knowledge and our vision for a bright future. Welcome everyone to day 8 of our Vigyan Yatra. I welcome our Chief Patron, Professor Nilamri Ben Dave Ma'am, Honorable Vice Chancellor, Saurashtra University, Rajkot. I welcome patrons Professor Chaitanya Joshi sir, President of Vigyan Gurjari, Gujarat Prant, Dr. Narottam Sahu sir, Advisor and Member Secretary of GUJCOST, Professor Girish Bhimani sir, Dean, Faculty of Science, Saurashtra University, Rajkot. Co-patrons Dr. Ramesh Parmar sir, Registrar, Saurashtra University, Rajkot. Our today's special guest, Professor Utpal Joshi sir, Professor, Department of Physics, Gujarat University, Ahmedabad, and President Akhil Bharatiya Rashtriya Shaikshik Mahasangh, ABRSM. Professor Bharat, sorry, Professor Bharat Kataria sir, Professor and Head, Department of Nanoscience and Advanced Materials, Saurashtra University, Rajkot. Conveners of GVS 2024, Professor Nikesh Shah sir, Head Department of Physics, Saurashtra University, Rajkot, and President Vigyan Gurjari, Saurashtra Prant, Rajkot. Professor P.N. Joshi sir, Secretary Vigyan Gurjari, Saurashtra Prant, Rajkot. Today's event coordinators Dr. Piyush Solanki sir, Assistant Professor, Department of Physics, Saurashtra University, Rajkot, and Dr. David Dhruv sir, Assistant Professor, Department of Physics, Saurashtra University, Rajkot. I welcome today's session chair, Professor Deepak Gadani sir, Professor, Department of Physics, Gujarat University, Ahmedabad. And I welcome our today's esteemed speaker, Dr. Balasubramanian sir and Dr. Vipul Kher sir. So now moving forward, I invite my senior lab mate, Ms. Neetu Chandravadia, to introduce our today's special guest.
Good afternoon, all of you. Myself, Neetu Chandravadia, PhD Research Scholar from Department of Physics, Saurashtra University, Rajkot. I would like to introduce the invited guest for today, Dr. Bharat R. Kataria, who is a professor and head of the department at the Department of Nanoscience and Advanced Materials, Saurashtra University, Rajkot. Dr. Kataria has a 16 years of teaching experience as assistant professor at Bowden Science College, Junagadh, Government Science College, Jalod, and Government Science College, Veraval. Sir is now serving at the Department of Nanotechnology since 2016. Dr. Kataria had published over 30 international peer-reviewed journals, Sir also have published over 3 books to his add. Dr. Katari is a vital part at various national and international conclaves. Now I warmly welcome Dr. Bharat Kataria sir to kindly share a few words and address the session.
Am I audible now? Thank you. Thank you, Ms. Nandini, for this kind of introduction of myself. First of all, the patron of this Vikas Yatra, GVS, respected VC, Gandhi Madam, the Dean, and Sir, and the invited guest, Professor Vikshit Bharat, and today's esteemed speakers, Dr. C. Balasubramanian, as I said, Dr. C. Balasubramanian from the FCIPT Gandhi, and another esteemed, respected Dr. Kheraj, who is an associate professor at SU, and uh, today's coordinator, actually, Dr. Dept from the Gujarat University. Fine. What to say about the Vigyan Yatra? Actually, every student, teacher, or a researcher is Yatri of Vigyan during his total lifetime. So, it is my great pleasure to speak in front of such an esteemed group of people who are deeply interested in the world of science. I think this is the eighth day of journey, Vikas Yatra, that is the journey through the wheels of knowledge, studying the edges of what people think actually, what they know, and pushing the limits of what is possible. So, why we are gathered here? Why? What is the importance of this kind of programs? Putting, getting people together is because collaboration and conversations are very important in ever-changing world of science, at least science. Not only we are here to watch, but we are also here to actively seek the truth and wisdom as a group. We all come to this platform with different ideas, different skills, and passions, which makes uh, our ideas, a bunch of ideas to be shared in the next few hours of to get the ideas more richer. As a work, as we work through the complexities of science or scientific research, let us keep in mind the main goal of our work is to solve the mysteries of science, to understand the nature's language, because the science is ultimately the language of the nature, and to use the power of knowledge to make a better place for living. It is impossible to say enough about the understanding of the science and to think critically in this time of the very rapidly occurring technological progresses and to understand the new world problems. As a student, as a teacher, or as a scientist, it is our job to encourage a culture of the intellectual curiosity and the empirical rigor to improve the also to motivate the next generation of the thinkers and the problem solvers. To make sure that the flame of scientific research stays lit for our future generations. We should encourage the people, and I'm sure we will do. We should encourage the people to ask questions, develop a never-ending desire to learn, and to aim for the excellence in our scientific work. As we start today's trip together, I want you to keep an open mind, ask the question freely, and work with others. Let us have a lively argument, share our thoughts without any restriction, without any hesitations, and push ourselves to think outside the box. This is what we are gathered here. As we share our ideas with each other, we will discover some new things, break down the words, and build a better and more enlightened future. Finally, I want to express my sincere appreciation to the unwavering dedication of this a large group of students. And I also want to thank the organizers of this event, Professor Nikesh Shah and Professor Joshi, and the coordinators, Professor Pius Solanki sir and Dr. David Dhruv for inviting me as a guest. Thank you. Thank you all.
Thank you so much, sir. Moving forward, I'm sharing my gratefulness in introducing today's speaker, Dr. Utpal Joshi, sir. Dr. Utpal Joshi is a professor at Gujarat University, Ahmedabad, at the Department of Physics, and president at Akhil Bharatiya Rashtriya Shaikshik Mahasangh. Dr. Utpal Joshi holds plentiful awards as well as fellowships to his name. A few to this add are DAE Young Scientist Research Award, Young Foreign Scientist at Japan, Boycast Fellowship by DST India, and many others. Apart from these, he have been an imperative body as member of governing board and member of governing council at Inter-University Accelerator Center, IUAC, New Delhi. You've been a fellow at GSA office and you've meticulously been the Senate member at Gujarat University. Dr. Utpal Joshi have had published a total of 33 publications in international peer-reviewed journals. He have worked with two research projects and guided over 11 projects in his field. All of this is just the very little of him. May I now please request Dr. Utpal Joshi sir to kindly take over the session with his remarks.
So,
Utpal sir, kindly unmute yourself, please.
Hello. Yes, am I audible now? Yes, so thank you for remembering us, Professor Mukesh Shah sir and his team for this wonderful organization of this Gujarat science, how it is excelling, and with Vigyan Gurjari. And we know that Vigyan Gurjari is a pioneer in taking up various, science programs, which actually does some work on the ancient Indian science, which have been forgotten, or people call it as mythological and other things. But the galaxy of the speakers that we have in this are actually, they are the very right people to give idea about their own research. At the same time, they have been working very hard to, get Indian science to further heights. So I remember my association with VIBHA back in when Oak was there. He used to come to us in Gujarat University with Vidyadharji, and we had one very nice, we call it as, Urja Yatra back in 2010-11, when it was in Ahmedabad. There was one Urja Yatra that was initiative by VIBHA, and we actually conducted in Gujarat University Physics Department, and that was very good success at that time. And after that, there have been so many programs, but I really congratulate Saurashtra University Physics Department and the entire team for taking up such a, on a large scale at a different level, this particular event with Vigyan Gurjari, and of course GUJCOST, who has taken keen interest in that. So my best wishes to all the participants, and really again congratulations to the organizers, Nikesh Bhai and entire team of Saurashtra University, who have been doing this. I know the guest of the speakers are really good. One would like to listen to them. Long association with Dr. Ganeshan and Pawan and other distinguished speakers, who, and definitely the viewers and the participants definitely going to get a big support and their knowledge. And of course the Vigyan Gurjari also can come up to our university, different places. We can plan some different out of box program as well, keeping in view a closed circuit in Gujarat, very active, and it is the demand of the time. So I congratulate once again, and I again thank the organizers for involving me into this wonderful event. Thank you.
Thank you so much, Joshi sir. We were pleased to have you today with us. Let me now take a moment to introduce the next speaker, Dr. D.H. Gadani sir. Dr. Gadani is a professor at Department of Physics, Gujarat University, Ahmedabad. Sir did his PhD in the year 2011 from the same institute, that is Department of Physics, Gujarat University, Ahmedabad, and currently serving at the same place today since 2016. Dr. Gadani also served at CU Shah College, Ahmedabad from year 1988 till 2016, for over 28 years. He is now at the university, Gujarat University. Dr. Gadani has 9 honors and awards at international and national level. He has been principal investigator in a research project by ISRO in year 2022. Sir share his vitality in various fields. He have been associate member at Gujarat Science Academy, Indian Association of Physics Teacher in year 2010, Indian Society of Remote Sensing in year 2015. Sir holds 51 publications in national, international journals plus conference proceedings. So now I kindly request Dr. D.H. Gadani sir to chair the technical session.
Thank you, Neetu Chandravadia, for introducing me. Before I start and introduce Dr. Balasubramanian sir, just first of all, let me thank Department of Physics, Saurashtra University, as well as Vigyan Gurjari, GUJCOST, for arranging a very good initiative of Vigyan Yatra for Vikshit Bharat, that is Gujarat Vigyan Sammelan. I congratulate the Department of Physics, Saurashtra University, and team of Professor Nikesh Shah for that. I can see that there are around 77 participants. It is a big number, and I have seen a list of authors who are going to present their ideas, and it is also very interesting. And today, I am fortunate to introduce Dr. Balasubramanian sir. Just let me give brief introduction of him. So he is currently Scientific Officer F at Facilitation Center for Industrial Plasma Technologies, Institute of Plasma Research, Gandhinagar. His current research activity and interests are synthesis and study of titania nanoparticles for its self-cleaning application in textiles, study of morphology and thermal stress-driven magnetism of magnetic nanoparticles, study of local atomic structure of magnetic nanoparticles by X-ray fluorescence spectroscopy, synthesis and study of semiconductor and metal oxide nanomaterials. After PhD, he was visiting faculty at Taiwan between 2008 and 2009. He was a researcher in Italy between 2006 and 2008, researcher in University of Rome, Italy between 2005 and 2006, and postdoctoral fellow at Italy between 2003 and 2005. During PhD, uh, he was a research associate at University of Pune, India between 2001 and 2003. He had junior research fellow on research project funded by Department of Science Technology between 1996 and March to September. He had junior research fellowship on research project funded by Department of Atomic Energy from December 1996 to September 2001, and research associate on research project funded by Department of Atomic Energy from October 2001 to August 2003. He has total 30 national and international publications. He has guided about 21 project students, and at present one student is pursuing PhD under his guidance. His hands-on experience is in designing vacuum chambers for synthesis of nanoparticles by thermal plasma technique. He has extensively used TEM, SEM, AFM, STM, XRD, FTIR, XPS, etc. He is also having experience on atomic emission spectroscopy, development of numerical code using Fortran to simulate the gas phase spaces concentration in thermal arc plasma synthesis process. He has 4 awards since 1989, National Fellowship awarded by UGC. In 2001, he got one award as a best student of international school and workshop from Italy. In 2004, he had one more award on nanotechnology and in 2010, he got MRSI prize for best poster paper presentation in April 2010. Uh, he has attended and workshops and conferences around 22. Number of poster presentations are 11. Number of oral presentations are 7. He has given more than 13 invited talks. and he got Doctor of Philosophy in 2003, Master of Science in 1995, and Bachelor of Science in 1989 from University of Madras. So I request Dr. Balasubramanian sir to start his talk. We are waiting for his talk, and we will enjoy.
Thank you, sir. Thank you, Chairman, sir, for your detailed introduction. I'm very happy to be part of this Vigyan Yatra. I thank the organizers, first of all, for giving me this opportunity to be part of this, and also participants. I hope they enjoy and they gain knowledge out at the end of this talk. Let me first share my thing, PPT. Should I share the entire screen? Yeah. Okay. Okay. Is this clear? Can you see?
Yes, sir.
Okay, just a minute. Let me first go to the entire screen mode. This. Okay. Now can you see the entire screen and the presentation mode? Hello.
Not yet. Still, it is PowerPoint presentation.
Oh, okay.
So
Just a minute. I should actually share the. Let me first open the thing first, maybe. Now can you see?
yes, now we can see.
Yeah. Okay. Thank you all. I think for your patient waiting. Basically, like when Dr. Piyush was asking me that day to give a talk, I was wondering, like, I'm sure that a lot of people must have already talked to nanoscience or nanomaterials. But then it's apparently not on plasma based nanomaterials. So I thought, okay, this is what I'm working on. So I'll present on this. But what I'll do is maybe this will be the contents of my talk. So basically, I'll touch upon some basics of plasma, or even before that, some basics of nanoscience, and then plasma, and then details of how plasma can be used for material processing, especially nanomaterial synthesis. I would say the participants, in case you have some questions in between, don't hesitate to ask. Raise your hands, or you can ask. I think so that, because it can be more interactive if you feel like it, if you want it to be. Okay. So basically, I'm sure that, like, for example, like, is the screen changing? Hello. Okay, fine. So basically, if you see that, uh, I think a couple of days back, one of my colleague, Dr. Mukesh Anjan, had given a talk on plasma, and it's like various applications of plasma, right? So basically, that plasma was more of, non-thermal plasma or cold plasma, where a lot of applications are there. But today's my is going to be on hot plasma or thermal plasma, where which can be used again for many applications. But I'll be focusing on the how to make different types of nanomaterials using this plasma. I'm very sure that not many people are working on this kind of in this area of plasma for nanomaterial synthesis. Okay, so probably when I talk about some of these basics of nanoscience, many of them you may be knowing, but you will have to bear with it. Just for the flow of it, I would like to touch upon each thing. Some of them I can skip, which based on fundamental things I can skip, because you probably may be knowing about it. So when normally what we do is, like, there are two things: nanoscience and nanotechnology. Many times people confuse nanotechnology and nanoscience because nanoscience is nothing but a study or a study of a process or property. It's a fundamental study that's being done. Whereas nanotechnology is something use of the processes, use of the materials developed, etc., for some application. So we should never confuse nanoscience with nanotechnology. So this I thought I should tell in the beginning. So because many times we see that course of nanotechnology, but that's more of application. There's more of use of the materials, use of the processes. Okay, so probably importance of nanoscale, you all know, but nowadays nanoscience is a very common area in most of the curriculum, academic curriculum. So basically what happens when you go to smaller and smaller size at the scale of nano or 10.9 minus 9 nanometers, minus 9 meters, properties changes drastically, physical properties and other properties changes drastically. Uh, and then you get new properties based on size and shape. Okay, like for example, changes this because of your changes in interaction between atoms and molecules. See, we all know in school we have studied like atoms, molecules, like more than one atom is a molecule, and then millions and millions of atom molecules give rise to solids, bulks, materials. Okay, so basically, like because when you go to nanoscience, the number of particles, number of atoms, number of molecules are much smaller. So you get property which are different from the bulk materials. Okay, so this is what the very fundamental thing which change difference which brings the nanomaterials the importance changes in properties. Okay, see what is the difference between a micro and nano? How do you distinguish? When can you say, like, for example, here if you see that smallpox virus is 0.2 microns or 200 nanometers, will you call it as a micron or you call it as a nanometer? The question always comes when you say 100 nanometers is nothing but 0.1 micron, right? So what is when can you call nanomaterial as a nano or call it as a submicron particle? So basically, if you see that when if you have the boundaries are defined by the behavior, if your behavior of your parsing is changes radically, then it goes to nanoscale. From microscale, when you go to nanoscale, the behavior changes. The objects that you're being studied, okay, behavior of the objects, how the object, like suppose you take a material, the behavior of the object changes drastically. Okay, then it's called as you have gone to the regime of nano regime. And if it doesn't change significantly, then you can still call it as a micro particle or microstructures. Okay, or either the behavior of the object changes or our behavior towards the object changes or our approach to must also, if it changes, then you can call it as a nanoscience. So this is the boundary which distinguishes between nano and micro. So what are the characteristics at nanoscale? There are big changes when you go of the object, when you go below 10 nanometers. Okay, so for example, people who are working in physics, they know that Newtonian mechanics and quantum mechanics. Like, so Newtonian mechanics deals with bigger objects, like isn't it? There are various other what you call underlying principles in that. We are talking about quantum mechanics. We are talking about small electrons, electron waves, clouds, etc. Whereas in Newtonian mechanics, we talk about objects which are detectable objects. So when you go from micro to nano, you're going from different mechanics altogether, different approaches altogether. And the other thing is, like, when you go to very small ones, nanoscale, for example, optical, like your electromagnetic spectrum, optical region of the electromagnetic spectrum, because of the diffraction limits, it cannot look into it. It cannot identify an object. So we have to go into something much more advanced, like for electron microscopes, etc. So when you go to nanoscale, it's not only the properties of the material changes, but your approach or your behavior to the property changes. The instruments or the technique that you use to study that also changes drastically. So this brings about a change in the regime, nano regime, micro regime to nano regime. So when somebody says what is the limit, like typically when normally we say that nanomaterials are 1 to 100 nanometers in size, it's a generalized statement. It's a generalized definition. Of course, it's not a what you call all encompassing, because for example, for ceramic nanomaterials where you have like aluminum oxide and titanium dioxide, etc., or those ones, like even if you have, let's say, 120 nanometers, 130, probably you can still call them as a nanoparticles or nanomaterials, because you are looking at the mechanical properties where the object's behavior does not change even at 100 nanometers, okay, compared to the micro. You get still you still get the properties of the nano regime. Whereas if you talk about semiconductor materials, or talk about optically active materials like zinc oxide, zinc sulfide, zinc selenide, etc., where you're looking at the optical properties. Probably even if it goes to 40, 50 nanometers, you may not be able to call it as a nano, because there the properties are not 50, 100 nanometers is not different from the micro. So probably you'll have to go to smaller size to go to see the drastic changes in its properties. So what I'm trying to say is, like, the definition of a nanoparticle, it depends on what is the application, what is the material. Okay, whether it's 1 to 50 nanometers, 1 to 10 nanometers, or 1 to 200 nanometers, it depends on that. That's a thing. So this is generalized thing. So what is basically nanomaterials? Let us say. So basically, it's like nothing but clusters. Few atoms, like two or more atoms or more molecules, forms a cluster. So nanoparticle can be considered a group of small clusters or atoms or molecules. When you have small clusters, maybe few atoms, a few molecules, a few hundred atoms, they exhibit novel properties, electronic properties, magnetic properties, optical behavior, etc. changes drastically. When you go to bigger clusters, millions of atoms, millions of things, then if the size changes, if the number changes, okay, then what happens? Instead of, then you don't see that, we see the bulk properties. Okay, you see the bulk properties of material. Basically what happens is, when you have small clusters, the interaction between atoms, interaction between molecules, individual interaction, they matter more than the what you call interaction between the overall group. It's like if you're a crowd, each member of a crowd will have certain characteristics, certain behavior, but a big crowd will have may have a different or averaged out behavior. So when you talk about bulk and when you talk about nano we are talking about individual atoms, individual molecules, or group or small group of atoms and molecules. They would be their behavior. In bulk, we are talking about long range order, long range interactions, long range properties. So that's the basic difference between small clusters and big clusters, or on the other hand, nanoparticles and bulk materials. So I'm just showing you the thing. Like for example, you have one atom or one thing. We have the atoms and molecules. So from single atoms to molecule, you go to clusters, and from clusters you go to solid state thing. So whether you do it through physics or chemistry, the cluster is the junction where it changes from what do you call single thing to a bulk material. So basically, if you see that clusters are the emergence of new properties, basically that gives rise to the thing. So of course, single atom molecule will not have anything, but the clusters have properties which is what we always look into. Okay. So chemical product cluster can be different from the constituent. Like for example, when you, I'll come to that. Maybe some example I'll come to later on. But properties of cluster can change drastically just by adding one single atom you add. It can change drastically. That's the thing. Like so, these are the things which you are looking into. It also provides understanding of the transition from single atom to molecule to solid state limit, like from the individual atoms to bulk. Clusters give you it's an intermediate state where it can give understanding of the various processes. Okay. For example, many of the what you call many body phenomena for bulk materials, like for electron conduction, band formation, superconductivity, it's all based on bulk properties, which may not be available seen in a single atom or a small clusters. When you talk about nanomaterials, there are two. How do you produce nanomaterials? Basically, as I said, atom or a molecule, few atoms or molecule. But if you're going to, are you able to see the cursor? Hello? Yeah, okay. So when you go from, when you go to higher and higher number of atoms, okay, you go towards when it crosses certain number, like millions of atoms, it goes to the bulk region, okay. And the nanometer, the cluster region, like single one is here, single atom or molecules is here. The in-between stage is the cluster region. Big clusters give rise to bulk region. Like small clusters, maybe few atoms, few hundreds of atoms or molecule give rise to small clusters. So basically, like if you see here, your nanometers comes in this region. Okay. So we can do this by two methods. One is you can approach it like you can start building up atom by atom or molecule by molecule and come to this central small cluster region. Or you can take a bulk material and divide it, break it into smaller and smaller, come to larger clusters and ultimately come to small clusters. So basically, if you see that there are two ways in which you can make nanomaterials. One is by building up from a small number of atoms or molecules and coming to a certain size, or breaking down, take a bigger one, take breaking down to a smaller size. So these are two approaches. So basically, if you see whatever methods of preparation of nanomaterials is there, it falls into one of these categories, which is called as building up process, or what you call breaking down process. So we'll come to that various methods which are uh, available for us and what is predominantly being used. Okay. So before we go into that, let's have a look at the why it has nanomaterials have got sort of importance. For example, we all know that most of the people were talking about nanotechnology, nanoscience, nanotechnology, nano, what to say, applications of nano. Okay, basically what happens when you go, as I told you earlier, and go to nano size, a lot of properties becomes changes drastic. It's not the value which changes; it's the property itself changes. So, for example, opaque substance like copper or titanium, they are opaque. They cannot light cannot travel pass through them. But when you take it to small size, it becomes transparent. So we are not talking about some change in values. We are talking about change in the property itself. Opaque becomes transparent. The inert materials like gold, we use gold and platinum because they are very inert. They do not react with ambient condition. They do not react with most of the chemicals. So because of that, we use gold ornaments and other things. But this same gold, when you go to small size, it can become highly reactive. It can be used as a catalytic material. So you see, there's a difference in the property, drastic change in the property when you just changing the size of the music. You're not changing the chemical composition. You're not changing any other parameter. Just decreasing the number of atoms or decreases cluster size of the atoms, cluster size of the particles. So basically, you decrease the cluster size, though, and then what happens, as I told you in the beginning, the interactions of individual atom, individual molecule, a group of atom, group of molecules becomes more predominant than the long range interactions. Okay. And then, for example, stable material like aluminum is a very stable. You have aluminum coating on many of the poles, electric poles, because it is very stable. It doesn't oxidize very easily. But that becomes combustible. It even in the exposed air, it can get catch fire. Iron is one of them which can catch fire when exposed at small scale. It can catch fire because of its reactivity. So as you see here, so the nanomaterials, the what you call the interest has has come only because of this change in size of the thing. Going to small size, it changes drastically. And I'm sure this you must have, I will not go details of it, but I'm sure that you all must have heard in one of your earlier or when you studied the all these nano properties comes from two predominant effects. One is a surface effect, other is a volume effect. When you say surface effect, when you any given material has got some surface area, in the sense that surface of the material will have some area and the bulk inside will have some occupy a certain volume. Okay, so when you break a material into small size, the surface area increases. Basically, if you say take this cube for example, if you have 4 centimeters, one of the thing, the surface area is 4 into the thing and 6 faces, so 96 centimeters square. Okay, so 4 square into 6 faces, 96. But the same thing if you break into two of 2 centimeters each, what you get the surface area is 192. Each one is smaller, 24. But then when you have 8 cubes, the total surface area is 192 centimeters square. So you see the surface area has increased drastically just by dividing it or breaking it down into smaller sizes. So what if increase the surface area, how does it why should it affect the properties? We'll come to that. Basically what happens when you increase the surface area, the number of atoms which are there on the surface increases drastically. The atoms which are inside the bulk, they are not exposed to the outer atmosphere, so they do not take part in any reactions, they don't contribute to any of the properties. But the ones on the surface, actually they're contributing to the various properties, various reactions, etc. So when you have more and more number of atoms on the surface, you have more reactivity, more interaction between the different surfaces. So these are the ones which are contributing to the what you call property changes. So as I said that when you go to smaller size, surface area increases, then obviously your interactions also increases. Okay. The next thing is volume effect. Volume effect is when the volume of a particle is small. Okay. What happens is the energy levels, the number of electrons, number of particles, number of charge is very less. So because of which you have a energy levels are very distinct. For example, like all electrons, if you have millions and millions of electrons within a certain thing, they are like a sea of electrons. The energies are much different. So there are always overlap of energies, or what you call close continuous continuum of energy. But when you have very less number of electrons, very less number of charge particles, then they are get separated. Okay, they get separated. So you have distinct or discrete energy. So there's a difference between a discrete energy and a continuum energy. For example, when you go to a small volume thing, the particle is smaller. When the particle is smaller than the mean free path of electrons in the electrical conductivity, for example, changes a lot. See, electrical conductivity, resistivity comes because there's a collision between the particles. So the flow of the electron is obstructed. But suppose if the mean free path is much smaller than the your particle size, then it can go from one end to another without any collisions. So conductivity increases. When the particle is smaller than the wavelength of light, then optical devices, in an optical device, then band gap changes. When you band gap changes, many of optical properties and other property changes a lot. And when you talk about magnetic properties, magnetic nanoparticles, when the domain is smaller than the material itself, then it's like every metal be a single domain. And when you have single domain, it's like you have the maximum magnetic properties, like for such what you call saturation magnet, everything increases drastically. For example, when I talked about band gap, if you see, this is a formula which is given by this thing. When you have the n, the lower denominator n is the number of particles, or number of charge particles or electrons. When this number decreases, the delta increases. So the difference between the energy level increases. So it becomes more discrete compared to the ones which you have when you have more when you are together, like a sea of electrons. So when you get a thing, like you can get a optical emission, like almost same as lasering action, even with the when you go to nano size. So these are a couple of examples which I'm sure you must have seen, like gold. Okay, gold yellow. When you have in bulk, you have it's yellow in color, but when you go to small nano size, it can have different colors. Okay, that's because, as I told you, the energy level changes, and what color you see is because of the emission, like absorption, emission, re-emission of light. So when your energy level changes, your emitted light color wavelength also changes, and you get different color of the materials. For example, traditional zinc oxide, which cricketers put it on their face, what you call for sunscreen lotion, they used to look white in color. But nowadays you don't see that because they use nano size. Because what happened is like it become transparent. Earlier, nowadays nano zinc oxide it is very transparent. So even if you apply, you don't see that whiteness. This is again another example how the same gold particles at different sizes, you can have different colors. Just because you change the size, you change the energy levels. Your energy level, you make it more discrete. So what has happened is you have got energy levels have changed. So absorption, emission, energy wavelengths are changed, and you get different colors. This other thing which is the surface area to volume ratio. I think I can just go through it quickly, because this I'm sure all of you know. But when you surface area increases, the volume decreases. The surface to volume ratio is something important. Like when you have 3 centimeter cube of the thing, and the surface area will be 3 square into 6 sides. Excuse me, 3 sides, so 54. Volume is 3 cube, 27. So if you take the ratio is 2. Whereas on this, when you decrease the size by, let's say, one unit, it becomes 24, and volume should be 8 actually. 2 cube 8. So 25 by 3, 8 is 3. Excuse me. So surface area to surface to volume ratio is increased by from 2 to 3. As you decrease, it becomes 6. So as you see that surface area to volume increases drastically when you go to smaller and smaller sizes. It all comes down to the same thing. Basically, what you have, the number of surface atoms at a small particles are very large, whereas at larger diameter it's very small compared to the bulk. And as I told you that If you have a if you have a what do you are quite spread out, whereas the third dimension is very, very small, very small compared to the other two dimensions. So they are called, like for thin films, nanoplates, those are all two-dimensional structures. When you go to bulk nanomaterials, they are having equal thing in all there, or what you call, you have aspect ratio, which is like 1:1. Then there are another class of nanomaterials called quantum dots. Basically, they are nothing but nanoparticles of semiconductor materials. So basically, when you talk about semiconductor materials, quantum dots, they are mostly, as I told in the beginning, they are mostly to do with optical properties. And I told in the beginning only that optical, thing, if the change in the property arises from the band gap. And so typically what you have, quantum dots are 1 to 10 nanometers can each होता है, because you have to have particles which are less than 10 nanometers to see the effect. More than that, you may not be able to see the effect of the nano size. If you have 40 nanometer or 50 nanometer zinc sulfide or zinc selenide, you may not be able to see as much the effect of the nano size as you see with a 5 nanometer quantum dot. As I told you, there are two ways of making it. One is top-down approach, is bottom-up approach. I'll just discuss a couple of them in each of them, then we'll go to the plasma process. In top-down approach, basically I told you that top-down approach is like you take the bulk of the material and break them into small sizes and then come to the regime of nano regime. So basically there are 2-3 ways of making. I've given only 2 of them, but there are other ways of doing it. One is mechanical process, where you actually physically break them into smaller, crush it, like you crush it like a powder, you crush it and take it to a small size. Okay, so it appears simple and straightforward. Obviously it's not very, so you would expect them to be used very well, and in the sense that widely used, but that is not the case, because there are a lot of limitations on that thing. Probably if you want to break them into, let's say, 50 nanometers or 70 nanometers, what is happening, like many of the materials may not be brittle, or so most of the material malleable. So whatever, if you crush it, it may not be breaking up, it may just get pressed into a different shape. Okay, so basically, like, so this process not commonly employed, but materials like ceramic materials like aluminum oxide and various ceramic materials, where if 100 nanometers is okay, this can be used. They call it ball milling method, where metallic balls are powder is kept inside that. They are rotated with a high velocity, crushing the powder particles into fine size. Okay, so typically those ones are brittle particles which can break down easily. The other process, electrochemical process. For example, you have a bulk material, you start etching out, or you start removing cluster by cluster, or layer by layer. So finally what remains is you have a surface which has got islands of small clusters, or islands of small clusters, which whose size would be in nano size. So then you can call it as a nano structured materials, which, like for example, porous silicon. You take a silicon, you add hydrofluoric acid and ethyl alcohol and pass some currents, few milliampere current. What happens? The surface gets etched out, forming different small islands in between, and these islands can give rise to nanomaterial properties. For example, emission properties, red emission, orange emission, etc. So this is used, but as you can see, that it cannot be used in every material. So for some materials, yes, this can be used. So the other method is like bottom up approach. Like you start from as I told you, start from the atom and molecule, start building up. So that is a process by which is actually widely used. In this, you have many different methods, like inert gas phase condensation, where what you do is you have a gas which you condense it in an inert atmosphere. So it's basically involves a lot of high vacuum conditions. Okay, and then start building up. So you create a vapor and then condense it. The other is plasma synthesis, which I'll be talking about, and then the other is laser ablation. Basically what you do is you make the bulk of the material, take it to gas phase. Okay, or and then start condensing them. So all this uses the same, that particular method. Of course, the other one which is commonly used is sol gel method, where wet chemical process. What you do is you take two chemical reagents, allow them to react with each other, and then when the products are formed, you products normally what will happen, the products will form and then they'll form a continuous layer or continuous thing. But before it react meets up with the third another product thing, you put a capping agent or a chemical which stops them from forming a bond, forming a sort of physical adsorption between two different products. So they call it wet sol gel process, where it's a completely wet process, and it involves a lot of chemical reactions and chemical thing. Okay. And the other is chemical vapor deposition, where you vaporize two chemicals, allow them to react, and then the products are settled on a substrate which is kept at certain temperature and certain conditions, where you get nano-sized particles or nano layers. So these are the, of course, this is not limit. I'm just giving you only some 4 or 5, but there are other methods also for this. So basically, we see that in what you call widely used methods are bottom-up approach. So where you actually start from an atom and molecule, start building up to a nano size. So if you talk about advantages, I just couple of them I'll tell you. In chemical vapor deposition is widely used employed method. You can do one dimension, like I said, one-dimensional nanowires, nanotubes. You can even do two-dimensional structures. For example, nanoplanes. You can do it, where you can grow nanoparticles or nano patterns. You can make it on a substrate. Okay. And you can have it. There are a lot of advantages. You can allowing them. You can grow them in a particular direction. You can grow them in a particular location, etc. The disadvantage is it uses a catalyst. Okay, if supposing if you're talking about your application, some biomedical application, probably the catalyst may not be a suitable one for biomedical compatible. So in that case, you have to be a little careful. So disadvantage is like it uses a catalyst, and so it can be you can have some impurity. Advantages are it can be grown on a pattern substrate, it can be aligned, it can be oriented, etc. And other methods, because these are two methods which are widely used in the in nanomaterials synthesis. The other method, sol gel method, advantages like you can make large quantities. Okay, you get very small size. If when I say nanoparticle is 10 nanometers, it may be plus or minus 1-2 nanometers, not more than that. So you can, and then particle size can be very small. You can go to 5 nanometers, 6 nanometer, 10 nanometer also is possible. It's not difficult. Okay, it's very good I think sol gel method. But disadvantage it's a chemical process. It depends on various materials. Like for example, for making zinc selenide, you may use a different process. For maybe zinc sulfate, you may have to use a different process. So processes vary from different what do you call, the process varies actually. Your apparatus could vary, you has to vary, and your entire sequence also will vary. Okay, and then other things you have to use a chemical agent for capping it. So your purity gets compromised. Okay, and also the process of making it can be it takes few hours to few days. So there's another when you talk about industrial scale production of nanomaterials, they cannot afford to wait for a few days to get the required quantity of powder. So this is something which is a disadvantage for the sol gel process. And the other thing is you need a post synthesis treatment. It's very essential because you need to, because they're chemical basically. You have to do washing, filtration, and all those things has to be done. So it involves a lot of chemical process, multiple steps, and each step can give rise to some kind of impurity creeping into the material. So these are the disadvantages of the sol gel method. So now let me come to the plasma thing. I'm sure you heard that day about what is plasma, etc. Just to brush up on that, plasma is nothing but the fourth state of matter, other being solid, liquid, and gas. In plasma state, everything exists in as charged particles like electrons, ions, etc. Okay, so it's not by definition it's a charged particle state. Okay, energy content in a plasma is very high. For example, like is higher than the other three states. Like the typical example, the standard example that we always give for plasma is like when you take ice, okay, which is a solid, which has got definite shape, size, and volume, etc. And it has got a temperature which is thermal energy, which is of like some value. You heat it, you melt it, you take it to the liquid state, water. This water has got a different volume, okay, and it got some thermal energy, some heat content, which is higher than the solid, right? So, and now you heat the water, it becomes water vapor, which is nothing but the gaseous state. And this water vapor has got a high, it may not have a definite volume, definite shape, but it has got very higher energy content compared to the solid and liquid, because you're taken into a vapor state for which you supplied energy to it, and the energy of the vapor is thermal energy of the vapor is much higher than your solid liquid. So basically your vapor contains more thermal energy. Okay, now the same vapor, if you are able to supply energy to it, okay, and then keep heating it, so that finally the water molecule breaks down into oxygen and hydrogen, and then ultimately breaks up into H plus electron, O plus electron. So what happens, you have a group of electrons and positive ions, and this, for getting this, you have supplied a lot of energy, and this energy is available with the system. Okay, so at a plasma state you have higher energy compared to the solid, liquid and gas state. And we all studied in school that energy can be converted from one form to another form. So when you are in a plasma state, when you have so much energy, and this energy can be tapped for various applications. You can use it for for optical, chemical reactions, what do you call mechanical or chemical energy. It can be converted in any form and then it can be tapped. Okay, and so, for example, all the stars and interstellar spaces, galactic space, intergalactic space, are in plasma state. It's only in terrestrial we have lightning and northern lights, aurora borealis, which is a plasma state. But man-made plasma is always seen in fluorescent lamp, etc. So basically, if you see that stars, they are all like high temperature thing. But in fluorescent lamp, the temperature is not there, but the energy is very high. That energy is in the form of kinetic energy. Okay, so the energy is very high, but in which form it is in depends on what it, like it can be form of kinetic energy, it can be form of chemical energy, it can be form of thermal energy, it can be form of other forms of energy. Okay, so when you have such a state where you have high energy content, very high enthalpy or high energy, it can be used for many applications. In plasma, can be used for CVD, plasma enhanced chemical vapor deposition, so you can make thin films out of it. Okay, you can do surface cleaning, surface functionalization, etc. You have material, you want to remove the oxide layer, you can do plasma cleaning of that surface. You can do implantation, you can use the ions in the plasma, you can accelerate it and then get the ions implanted or impregnated in the material, in the your substrate. So that can be done in the using plasma. You can use surface aberration, you can do metallurgical application. For example, operating, like you have big ores, you can evaporate it, you can heat it and evaporate it. So basically you can use the heat energy of the plasma to to do ore processing, all this mineral ore processing, etc. And the other thing is, like, you can grow nanomaterial using this. So basically, like, what you do, nanomaterials, you evaporate it and then deposit it on a substrate or on a medium. So if you talk about the process of this, how do you make nanoparticles by plasma process? So basically what you do is you create a plasma between two electrodes. One of them is a cathode, which is negatively charged electrode. Other is anode. Okay, so basically you strike an electric arc. It's something similar to a spark, which is spark is momentary, whereas electric arc is something which is continuous. You strike an electric arc between between the negative potential and the positive zinc. You have a zinc, and this contains you get this arc only because it's all ionized state, and this has got high energy. So this one instantaneously evaporates this material. Whatever is kept here, it evaporates, because the temperatures can be few thousand Kelvin, maybe 5,000, 10,000 Kelvin. In that temperature, anything will evaporate. So basically what you do is you are evaporating this material, and this goes to gas phase. But as it moves away from the gas phase, it starts nucleating, it starts condensing, it's agglomerating and coalescing. So what happens is, like, you have created a material from a solid state, you created a material into vapor, took it to vapor state, okay, instantaneously. And then, because what happened, once it comes out of the plasma zone, the temperature is very, very less. So and then supersaturation takes place, and you get nucleation and growth. and then you can get difference. If you allow it to continue, what will happen? This particle will grow into a big size particles, micron particle. But what you can do is you can always stop the growth. Maybe at this zone or this zone, you can stop the growth by, see, the growth is taking place because of thermal energy, heat energy. Suppose you take away the heat, either at this location or this location, you take away the heat, the growth will stop. Okay, so basically what you do is you have high temperature at this part, which helps in evaporation, but immediately after that, very close to the sea, you have a very low temperature substrate or a surface which has got a very low temperature, very close to room temperature, which will arrest the growth of the particle. So you vaporize it, allow it to nucleate, allow it to grow slightly, and then stop the growth. So, and then you get particles of very small sizes. Could be 20, 30 nanometers, 40 nanometers, depending on how quickly you quench the heat energy here. So the advantages of plasma method is it's a high temperature process. So you can, temperature can go up to tens of thousands of Kelvin. So you can do any material, which material, doesn't depend on the material. Even ceramic particles can also be synthesized, nanoparticle can be synthesized. Plasma is a powerful medium to promote high rates of chemical reactions. So when you are in ionized state, what happens is the reactions, the plasma chemistry is completely different from your normal chemistry. The reaction which are not possible in normal temperature, normal this thing, can also happen at very high temperatures when you are in ionized state. So you can promote a lot of chemical reactions, which is generally not possible in normally not possible in a low temperature process. And then the purity of the products is there's no very high, because you're not using any capping agents, you're not using any catalyst to grow the, unlike in CVD, unlike in salt gel. So basically what is happening, your whatever your raw material is pure, this one is pure, your product is pure. Okay, and the thing is, like, you don't, since it's being done in a one step, but what you're doing is basically you are evaporating and condensing. It's a single step. You evaporate it and condense it. It's not a multiple step. So what is happening? Number of steps involved in making the product is just as one step. So your impurity is very limited. Okay, and you're talking low synthesis time scales. Unlike salt gel, where you need hours or days, here we are talking about minutes. Okay, because what is happening, plasma is high energy, so as soon as you switch on the arc thing, it instantaneously, maybe in a few seconds, it evaporates. Once it evaporates, when it comes out, it starts condensing. So it's an instantaneous process. So typically the time scales are at minutes as compared to chemical methods. The other important thing is, like, since the high temperature, you will get highly crystalline products. Unlike amorphous products are, which has got very different kinds of applications. And also the other thing is, like, since it's high temperature, you have very high temperature the core, and within a few hundreds of microns, you have very low temperature. There's a sudden thermal quenching is there. Sudden thermal fall of temperature is there. So that gives you thermal stress in the system. Your nanoparticles have some amount of stress in the thermal stress, which can give rise to dangling bonds, free dangling bonds, or it can be used for very functionalization. It can be used for many other applications. So this is one of the advantages. Maybe not all, but quite a number of them you can use this property for some applications. And then you can, of course, you have many different types of parameters which you can do, like plasma you can vary different parameters, and then just anyway, it's like more like salt gel. Salt gel, you can vary the concentration, you can vary the normality and get different products. Here also you get many parameters that you can control, like plasma current, plasma volume, temperature gradient. You can control that. So plasma, the other thing is, plasma can be created in gas made, and also it can be created in liquid medium. So as you can create a plasma, what I showed earlier was in a gas phase, but you can also do the same. You can do the arcing in a liquid. You can insert two electrodes maybe in a water medium and strike electric arc between the electrodes. So what happens? You get a plasma inside a liquid. So what is the advantage? The density of the liquid is anyway much higher than a gas phase. Okay, and your quenching effect will be different compared to your gas phase. So you can have different morphological features of the nanoparticles, nanomaterials. You can also get different chemical composition of the nanomaterials. So basically, so same material, you do in a gas phase, you can get a different size and shape. Or you can do it in liquid medium, you can get a different size and shape. Of course, there are various challenges in doing it in a liquid medium, for no doubt about it. Controlling the thing, how the liquid vaporizes, etc. But people have done on that, and they were able to get different thing. And you can also get metallic nanoparticle without using any helium or without doing any high vacuum conditions, because if you're able to control the thing, there are no chemical reaction taking place in the thing. You can get particles which are inside the liquid, which will not get oxidized. So basically, when we talk about nanoparticle growth or nanoparticle production, it all depends on nucleation and growth of the nanoparticles. Basically, the cluster formation, the number of clusters, the number of type of clusters. So basically, if you do it in a thing, depending on the quenching, thermal quenching, density of the medium, etc., you can have different clusters, cluster sizes, etc., and you get different types of morphological features of nanoparticles. So this is one of the plasma. So using plasma can be done gas made and liquid phase. There are various parameters that you can control, like plasma current, medium, gas temperature, etc. So I just show you some from the literature. Like even in this one, when you talk about liquid, you can keep two electrodes within a liquid, and you can have different types of electric cars. Each one has got some advantage and disadvantage. You can have all these types of things, and of course the liquid medium itself can be changed. You can have different types of liquid medium, and you can have even a reactive liquid medium. So you see that you are able to, and this all the instantaneous process. You strike electric arc, and depending on the medium, depending on the electrodes, depending on the thing, you get different materials, different shapes, different sizes. So this is like, even in a liquid, you can see that particles start floating or get suspended within the thing, and you can have particles precipitate. And if you analyze this, they'll have different sizes, shapes, and also the chemical composition. So you see, in a given this thing, you can have different products. You can separate out them from the different levels in the water. I'll give some examples of the what do you call using plasma in a gas phase experiment. Different, what all things you can get, different sizes, shapes, and also crystalline. Using the same materials, everything same, just by changing the plasma current, you can get different crystalline phases. Like this all related to one particular phase, cubic phase. Okay, and if you change the current, you get mixed of cubic and hexagonal. If you change the current further, you get, like you see that this one which is not existent there, it starts coming up. So you can actually your unlike the chemical methods, your apparatus is same, your process is same, your time scales are same, nothing is changing. Just changing the parameter, you can get different types of what you call different crystallinity of the product. If size and shape, like you see spherical particles here, nothing, everything is same except for the current. Is I change only the plasma current. So what is happening? You have spherical particle, you have distorted spheres, you have hexagons. So you can see the hexagons here. So you just change the thing. You can get with the different aspect ratio, long wires. You can get also the hexagonal shapes. So you can get here. You can see that particles are there. You have wires are also there. Of course, for if you have both together in the same product, then how do you separate it out? Yes, there's always a question. But you can always control this thing so that you can get only this or only that. To a certain extent, not 100%, to a certain extent, yes, you can do that. I can get different shapes also. Like these are nanocoils of the same material for different parameters. Like this, if you see here, these are nanowires, and then the same material you can get nanocoils. So basically, that all depends on the what do you call the nucleation growth. And nucleation growth is decided by not only by the material, but also the thermal the thermal temperature availability, the quenching, and the growth mechanism. We were able to get cobalt oxide nanostructures of cubic shape cobalt, which is we could get almost quite a lot of cubic shape, unlike the spherical particles. So as you see here, this iron oxide, I'm just trying to show you, like you can get different shapes and sizes for the same process, for the same apparatus, of different materials and different morphological features. You see spherical particles, you can also get, in a different process, you can get parameters, you can get purely hexagonal shapes. You can get plates, hollow plates of the same material, and also you can get core shell particle. You see, you have an iron oxide particle, you have core iron, and you have the oxide layer on the zinc, and it's very much seen here. You can see this one. All of them have got a inner core different and outer shell different. You can get single crystal, like as you see here, high resolution TM. We can see here, they are like it's a single particle with a high single crystal material. So, and I would say that, see, all this nano science has developed basically not just because, not only because of the advance, but it's also the advances in instrumentation techniques. Probably, like, we all know that nano structures are seen in nature also, but this field of nano science has advanced the last maybe 40 years or something, because it's advances in the techniques. Like, we are able to have techniques which were able to use it for seeing them, for studying them. So I just briefly touch upon the techniques that we use for the thing, which has helped in advances of the nanoscience or nanotechnology. Okay, so typically what you use is X-ray diffraction, scanning electron microscope. I'm sure all of you know this one. Transmission electron microscope, atomic force microscope, STM, BET, Raman spectral for it. So probably one or two of them we can touch upon. So if I take a electron beam, for example, and if the electron beams interacts with the specimen for on a thing, what all you can get? You can get the one which is backscattered or reflected. That can give rise to SEM. When it goes through, it gives you a transmission electron microscope and its properties. And you can also get, like, depending on how it is, whether you take backscattered electrons or secondary electrons, you can get yields, you can get different type of chemical composition, morphological features, all those things we can get. So it's basically, if you see here, depending on what energy of the electrons, the energy of the material, thickness of the material, you can get different types of instrumentation and the property that can be studied with that. Just briefly talking about SEM, I'm sure SEM you all must have used, many of you must have used. Basically, it's a very low energy, in the sense, compared to TM, it's a low energy, 30 kilo electron volt. You can see features of around 25-30 nanometers. Traditional filament. If you talk about lanthanum exoborate, maybe you can go to slightly better resolution, and in the field emission you can go to even better resolution. You can also use not only for seeing size and shape, but also you can use it for seeing the chemical composition, relative chemical composition of the materials, of the elements. The transmission electron microscope is nothing but the same. You use electron beam instead of the optical beam that you used in an optical microscope. Only difference between SEM and TM is transmission electron microscope use a high energy. The minimum is 80 kilovolt, maximum can go to 300 kilovolt. So when you go to higher and higher energy, what happens? The wavelength reduces. Okay, so it's able to interact with the smaller size particles. Basically, when do you see an object in a microscope? When the wavelength of the probe is almost the same order of magnitude as the material that you are studying. Suppose you have a 100 nano, 1 micron particle. You have to have a wavelength of the probing wavelength should be at least microns, less than equivalent close to a micron. If you're talking about nanoparticle, you need to have wavelength which is much smaller. Okay, so then interaction between the electromagnetic and the interpreted wavelength and the matter is very important. So when you go to higher energy, you can go to smaller wavelength. You can see smaller objects. Okay, of course, it has got its challenges, because SEM sample preparation is very not difficult, whereas TM you have to prepare very easy. It has to be electron transparent. The electron beam has to pass through it. If it's thick, obviously it will not pass through. So your sample thickness has to be very thin, and you have to make sure that your sample is scattered, dispersed uniformly and well over the entire area, scan area. And you can also do using the same instrument TEM, you can also do a selected area diffraction, which will give information about the polycrystallinity, single crystallinity. In fact, it will also give you D values, interplanar distances, just like your X-ray diffraction. Atomic force microscope is something which is very common nowadays, because it's not very expensive, and it doesn't require high vacuum, it doesn't require AC, but you can do a lot of things with AFM. It's a versatile technique, and you can see things in the scale of nanometers for sure. And it can be used to study many different materials. You don't it need not be electron transparent. It need not be what do you call, any particular conducting, non-conducting. It doesn't matter. You can do various types of study, and you can also do a three-dimensional imaging of that. Unlike your SCM or TEM, where you do a two-dimensional analysis, here is a three-dimensional, and you don't require any specific sample preparation. So you can also do solid and liquid surface can be seen. You can also see biological samples. So it's very easy. So if you see here, you have a substrate, you sample, okay. You have cantilever, but it's fixed at one end, free at the other end. There's a laser which falls on that, and as the forces between the atomic forces between the tip and the sample gives rise to vibrations, oscillations of the tip, and these oscillations are the laser falls on it, and this tip oscillates. The photodiode position, the photo signal changes its position, which can be fed into an electronic circuit, and then it gives you the what do you call the mapping of the ups and downs, basically the surface roughness, surface topography. So this is what a simple principle of AFM, and it's very versatile. And of course, the other one is similar to AFM, but uses a probing, what you call, conducting medium. You can have SCM, scanning tunneling microscope, where actually you can see very, very small objects. You can go to angstrom level, where if your tip and your, what you call, if your tip is conducting, and your sample also has to be conducting. So what happens? There's a gap between the very small gap, maybe a few angstroms. The electron tunnels from your tip to the or vice versa, and that current can be measured, and that can give you information about the surface roughness, etc. So basically, if you see that STM and AFM are very room temperature, atmospheric ambient conditions, and can be used to study various different surfaces at a very small. So X-ray diffraction anyway is thing which can be used for crystallite size analysis. So what I would think is like basically, if you see here, this is the technique that we use typically, but there are other techniques are there. For example, like surface area analyzer, etc., which can be used for studying nanomaterials. So I stop with this very fast presentation. You can ask questions if you have. Thank you.
Thank you, Dr. Balasubramanian. It was a very nice and interactive talk. I would request participants to have any questions. They can unmute themselves, or they can write the question in the text box. You can either unmute yourself or write the question in the text box.
Good afternoon, sir. Am I audible?
Yeah.
Sir, it was I have done PhD in nanomaterial synthesis, and it was a really, really informative and good session. I wanted to just say thank you for taking out time for such a informative and knowledgeable session.
Thank you.
Yes, anybody else, if you want to ask any questions, or you may ask, or you may write in the text box. Okay, I think no other question.
But they understood everything, or they did not understand.
No, actually they understood everything, and that I thank Dr. Balasubramanian sir. You gave a very interactive and interesting talk on plasma in nanomaterial synthesis. You started with the nanoparticles, how the nanoparticles are formed, how you can analyze, and what are the properties of nanoparticles, and how the properties change, and you can say how can you differentiate between micro and nanoscale. So Newtonian mechanics just goes and quantum mechanics come in. That is the best way, and it was really interesting. And by looking by hearing you, I was thinking about my class, that when I go to my class, a number of students are there, so that is like a classical mechanics. But when they come individually to us, the behavior also changes.
Changes, exactly.
So just I was correlating with your talk, but you gave very much interesting talk. Also, you gave the information about how to make the nanomaterials by bottom-up technique, or you can uh, disintegrate the big materials to obtain the nanoparticles. What are the surface effects, volume effects of the nanoparticles and materials? Your way of presentation was very lucid, sir. Really, we are delighted, and you gave very much suitable illustrations also in between the talk. You also explained the use of the SAM, TAM, XRD, etc. In a very lucid way, and how we can proceed towards the plasma physics. That was a really interesting talk by you. And on behalf of the organizers of this Vigyan Yatra, Vigyan Gurjari Department of Physics, GUJCOST, I thank you for
Thank you.
delivering
Thanks a
a
lot.
very nice talk. On
Thank
behalf,
you. Thank you also for the participants for patiently
yeah,
listening to this thing. Yeah, thank you, sir.
thank you so much,
Thank
sir.
you. Thank you.
Uh, now,
So
yes, sir.
I can log out, right? This isn't it?
Yes, yes.
Thank you.
Yeah.
Thanks.
Thank you so much.
Thank you, sir.
So now I would like to invite another speaker for today's talk, Dr. Vipul Kheraj, sir. Uh, yeah, he is here. So just before he starts his talk, let me give a brief introduction of Dr. Vipul Kheraj, sir. So he obtained his PhD in applied physics from MS University of Baroda in 2008 before joining SVNIT Surat as assistant professor in physics. Currently, he is working as associate professor at the Department of Physics, SVNIT Surat. His areas of research are thin films and material science, with an emphasis on optoelectronic materials and devices. Dr. Kheraj is Fulbright alumnus, being a Fulbright Nehru Postdoctoral Research Fellowship awardee for 2013-14 at University of Utah, USA, to carry out research on cost-effective solar cells. He has published more than 60 papers in high-impact international journals and has written a few chapters in various books. He has also worked on quite a few sponsored research projects with a total grant exceeding rupees 3 crores from the reputed funding agencies such as GUJCOST, DST, DAE, BRNS, etc. He has also been involved in various administrative portfolios. He served as the head of the Department of Physics SVNIT from 2015 to 2019 and subsequently got appointed as Associate Dean of Faculty at SVNIT Surat from 2019 to 2022. Apart from research and teaching, Dr. Kheraj is a very keen science communicator and he has been actively involved in science outreach. Currently, he is the chairman of the Physics Club of SVNIT Surat. So, with this brief introduction of Dr. Vipul Kheraj, I invite him to give his talk. Thank you, Dr. Vipul Kheraj.
Thank you, sir. Thank you so much. Am I audible?
Yes, you are audible.
All right. So I will first share my PPT and all right. Is it visible on the screen?
Yes, it is a full PowerPoint presentation is visible,
Yes, sir. Okay.
but PPT is not visible. Or
Yeah.
whole thing is visible.
All right. How is it now, sir?
Still not visible.
Hello.
Yes.
Yeah.
Still, the PowerPoint presentation completely is visible, not a PPT.
Okay, I need to, I think.
You have to press that upside arrow.
Is,
And from that, you will get. First of all, you have to switch on the PowerPoint slide.
yeah, so it is full screen on my PC, but I'm not sure if it is
So
full
just
screen.
you can press Alt tab, and then you will be able to select the PPT.
I think, yeah, entire screen would be better. Yeah.
Okay, then also it's
All right. So now you can see my entire screen, I guess.
yes. Now PPT is visible.
All right. So thank you. So I'm sorry about this, and thank you so much for this invitation. It is actually a pleasure for me to be able to share my views and whatever I feel exciting about the science and technology with the students and participants of this event. And I also wish to congratulate the physics department, Saurashtra University, and the GUJCOST and this Vigyan Yatra program and Physics Gurjari organizers for this wonderful event. Um, I always believe that something which is lacking in our society and requires more efforts from the teaching communities or science communities is the science outreach. So thank you very much, sir, and the entire team of Nikesh sir, Piyush sir, and all the faculty involved in this event. It is indeed a wonderful initiative, and I'm glad that I'm part of it. So thank you so much, sir. Also, when Piyush sir called me for this talk, and he was like kind of discussing a couple of possible dates, he first said 14th, and I was like, I didn't even listen to the next date. Like 14th is final, and there's a reason for it. The reason is in the photograph before you. So of course, this is not the live one. This is on. I mean, this is not the physical talk. This is online. So I will refrain from asking a lot of questions. Otherwise, I have this habit of asking a lot of questions to my audience. So yeah, I mean, I would answer here because it's online. The boy on your screen is Albert Einstein. Right. And today is his birthday, 14th March, also known as Pi Day, 3.14. So, the moment Piyush sir said that, 14th could be one possible date, I was like, okay, fix it. Like, I'm fine with that. And I'll be speaking on 14th. And yeah, so this is like, there cannot be a better day than this to talk about the topic that I'm going to talk about. The topic that I would generally present in a such an outreach event or in conference would be solar cells, right? Because that's my area. Like I work on the materials for solar cells and the photovoltaic things. I'm basically an optoelectronic materials person, so I would prefer to talk on semiconductor materials and solar cells and thin films. But luckily, just the talk before mine was a wonderful, brilliant talk by Balar, and that covered a lot of material science and plasma assisted material synthesis. So, my part is covered kindly, even in a better way than I could have presented. Thank you, sir. But what I'm going to talk about, am I audible? I'm sorry, just to confirm.
Yes,
Yeah,
you
and
are audible.
everything is okay, right? All right, thank you. So yeah, since this is 14th March and this is an outreach event for students, I thought let me talk something about more exciting science, about more interesting things in the history of science, and something which is attached to Albert Einstein. Something which is related to Albert Einstein. So I thought I would talk about solar sails rather than solar cells. Solar cells is a very interesting concept, and then I was preparing the talk on solar cells and realized that probably Einstein would be more happy if I kind of extend this concept and talk about one object which he was the most fascinated person about, and that object is light. And Einstein had written several times that the light is the most fascinating object or thing in the universe, right? So I thought, I will cover the solar cells, but let me kind of generalize it and talk about the light as our probe, or like let us pursue the light in the in the exploration of the mysteries of universe. So with that idea, I ended up making the PPT on this topic, which is pursuit of light. We will be using the light as a probe to get enlightened about the universe. So, and this picture is like this photograph on the screen is from a very famous movie, Interstellar, and we will, if time permits, talk a brief about it. All right. So objectives are very simple. As I said, the talk before mine was very technical one. With a lot of details about the material science and plasma and the technologies surrounding it. Mine would be more about a popular science topic, a talk where we won't be discussing a lot of mathematical part about the physics of concept we are talking about, but we will talk about the significance of it and somewhat we will deep into the history around it. So this is more, as I said, is a science outreach talk or a popular talk. So the objectives are simple. Let us realize that light is fascinating, as Einstein rightly said. The universe keeps giving us clues to get itself explored, and we will see how we got some very interesting results. And then we'll do this through these two case studies. We will take first the case studies of gravitational waves discovery, where light acted as a prop for us. And second one is for interstellar explorations, like we are fed up with the Earth, or probably Earth will get fed up by us very soon. So we want to find a new home, and that can be distantly possible if we use light to ride over it. So with these two interesting case studies, we will try to realize how amazing the light is. And through all this, we will keep the bottom line as following that physics, or in general, science is fun. Right? We want to keep science interesting so that more and more students get into science and help the humanities eventually. Okay, so let's start. As I said, we will try to attain the objectives through these two case studies. So let's first start with the first case study, which is about gravitational waves. And as I said, it's the birthday of Albert Einstein. He is the one who kind of stimulated the area around gravitational wave. In fact, a lot of resources report him as the first predictor of the gravitational waves, which is not technically correct, and we will see how. But when we think of Albert Einstein, we think of a few specific terminologies, one of them being the gravitational waves. So I thought let's talk about the gravitational waves from Einstein's perspective. And as I put the first photo of a very childhood pic of Einstein, around 5 years age, I thought, let's see how he evolved. Eventually this is the picture we know him by, and he born on 14th March 1879. Okay, and when did he come into the limelight? He came into the limelight in 1905 when he presented those 5 groundbreaking, brilliant papers. I mean, me as a researcher, when I think about, four groundbreaking papers in a year, it hits me hard. I cannot even think of 2-3 good papers, that too in a narrow area of my research. And here we have a person presenting 4 or writing 4 papers in 4 relatively different areas of science, and all of them are kind of groundbreaking in that regime. So that's when he came into limelight and kind of took over the scientific community in those days. And of course, these all things were groundbreaking, but it all started when Einstein imagined chasing after a beam of light at the age of 16 years. And that's why that's probably the catalyst for me keeping this title as The Pursuit of Light, because he wrote it. He wrote in his autobiographical notes much later in 1940s, I think. In 1949, he wrote that a paradox upon which I had already hit at the age of 16. If I pursue a beam of light with the velocity c, which is the velocity of light in vacuum, I should observe such a beam of light as an electromagnetic field at rest, though spatially oscillating, right? So basically the idea is, like, if I am traveling with the speed of light, parallel to speed of light, then the light would appear to me as stationary. I mean, in those days, the common notion was that if I travel with light parallelly to it at the speed of light, then I would feel as if the light is stationary. It is just oscillating in space but it's not moving ahead because I am moving with the same velocity. And he said that this would be the common perception, but there seems to be no such thing, however, neither on the basis of experience nor according to Maxwell's equations. So he said that this is not going to happen. From the very beginning, it appeared to me intuitively clear that, judged from the standpoint of such an observer, everything would have to happen according to the same laws as for an observer who relative to the Earth was at rest. So, but how should the first observer know to be able to determine that he is in the state of fast uniform motion? So basically the idea is like, if you are traveling in a non-accelerating way at a uniform speed, then you are in an inertial frame, and everything should behave exactly the way it behaves on the Earth, or when you are stationary with respect to the Earth. And one sees in this paradox the germ of the special relativity theory is already contained. So at the age of 16, when he was doing this thought experiment, and Einstein was famous for thought experiment, so he said, when I was doing this thought experiment of traveling with light or pursuing a beam of light, the idea of the special theory of relativity kind of jumped in when I was 16. And this was written much later in 1949. And then eventually he came up in 1905 with this idea of special theory of relativity, where he developed that entire theory. And the theory was kind of based on a very simple only two postulates. And these two postulates, like, these are things we know already. Like, I'm not saying anything new, but these are the base that we will be building upon. So the first postulate says that the laws of physics are invariant in all inertial frames of reference, right? That's what he meant when he said in that note that when I traveled with the speed of light in my mind, I understand that the laws of physics would not change if I am in an inertial frame. And that was the first germ of special theory of relativity. The second postulate that he built his theory upon was the speed of light in vacuum is the same for all observers, regardless of motion of light source or observer. Whether the light source is moving or the observer is moving, the velocity of light will not change in vacuum, and it is the maximum velocity of light. In fact, the first one was originally proposed by Galileo, and he just kind of rephrased it as a postulate for his theory. The second one was his original idea that the velocity of light remains constant. In fact, to my young friends in PG or early PhD, a very interesting way of looking at this is that the c, which is a constant, which is 3 × 10⁸ meter per second, is not limited to the velocity of light, although we know it as the velocity of light. Somewhere Einstein wrote it, and I don't remember where, but I have read this, that the velocity of anything, the maximum velocity of anything, the maximum velocity of information in universe is c. Light is just one case, right? So the c is actually a universal constant which defines the maximum limit of speed at which something can travel, light being one of them, which usually travels at that speed. There are some other things which usually travel at that speed, c, and we'll talk about them in a very few minutes. All right. By the way, another question that I would have asked had it been the physical, talk, that what do we mean by spatial? Like, what does the term spatial, indicate in the special theory of relativity? What was special about special theory of relativity? Anyways, I'll answer in a few minutes. Yeah. So after, he built up this special theory of relativity based on those two, postulates, there were several predictions which resulted from the theory. One of them being simultaneity of the events, right? In our normal day-to-day life, we have this exact sequence of events, one event happening after the other, and the other event happens after the next. So it's like, so we have a sequence of events. But, the special theory of relativity says that this sequence need not be same for all people at different space, in different position of space. Depending on how they are traveling, this event sequence might change. And Einstein explained it based on this famous thought experiment of traveling in a train. And he said that if I'm traveling in a train and I turn on a light source in both the directions, the light that is, because light travels in both the directions at the same speed, the one that is traveling backward, the back extreme, because it is also coming towards the light source, from the point of view of an observer who is stationary on the platform. The observer on the platform would feel that the light is hitting the back end first and the fore end, the front end later. So this two simultaneous events, which are simultaneous from the point of view of the person in the train, may not be simultaneous from the point of view of someone who is in the other frame of reference. So yeah, this is one thing which was the outcome of the special theory of relativity. Another one was the length contraction, and then the third one, which is my favorite, is time dilation. The Einstein proposed that the time slows down as the velocity increases and as it reaches or approaches towards the velocity of light. We call the maximum velocity c. And many such outcomes were predicted by Einstein as a result of the special theory of relativity. One of them is like this famous twin paradox. And again, had it been a physical one, I would have asked what twins paradox is, because it's very interesting. I have realized that although all of us know the twins paradox, many of us have not properly comprehend the paradox and what the paradox part in it is. Because the time dilation equation exactly predicts how younger the person traveling with the speed of very high, at a very high velocity in the spaceship would be as compared to his twin on the Earth. We know we can calculate exactly how younger would the person traveling in spaceship would be, and if it matches, there is no paradox. So the paradox is not that the two twins who born together would be at different age if one goes in the space and comes back. That's not the paradox, because that can exactly be calculated from the equation. The paradox lies in the fact that if both of them are traveling with the same uniform velocity, not same but uniform velocity, one is on Earth and the other one is in the spaceship and is traveling at a constant velocity, then these two frames are inertial frames, and from the point of view of the person in the space, it can easily be perceived that the guy on the Earth traveled at a very high velocity with reference to the person in the spaceship, and in that case the guy on the Earth would have aged or should have aged lesser, because the guy on the Earth traveled at a very high speed. So that's the paradox, who would age lesser. Anyways, we're not going into that detail, but Einstein did not stop there. He wanted to include the general, he wanted to include the gravity into his theory of relativity, and so he came up with the general theory of relativity 10 years later in 1915, and he reformed our understanding about the gravity. So now Einstein proposed that gravity cannot just be considered as a force, but it can also be perceived by means of a space-time wrap, or a space-time which is a single entity, and the mass defines how the space-time would kind of curve. So gravity is built into the actual structure of space-time. The gravity is universal, right? And space and time are curved. Nothing can avoid feeling that curved structure, not even the light, right? But remember, the light cannot change its speed in vacuum. That was the first postulate of second postulate of special theory of relativity. So even if light curves because of the mass, curving the space-time, the velocity of the light cannot change, which means light must bend along with the space-time. So that causes, so the outcome of the general theory of relativity is that if the light travels through a curved space-time, it would bend. It would not travel in a straight line, which was kind of a revolutionary in those days, because the light had always been thought of traveling in a straight line in the line of sight ways. And here we have the Einstein telling the world that the light can bend without anything in vacuum. Light can bend in vacuum if there is a very strong mass around it. So overall, if we sum up, the special theory of relativity and the general theory of relativity, these two very interesting outcomes are that the velocity slows down the time. The higher the velocity, slower the time. The gravity slows down the time by means of curving the space-time. So higher the gravity, which basically means higher the mass around it, the slower will be the time. And both of this can be exactly calculated using these equations from the special theory and the general theory of relativity. Am I online? Is that fine? Because since I am sharing my entire screen, I cannot see the.
Yes.
Yeah. Okay. Thank you. So yeah, so with these two equations, we can exactly calculate how the time would change, how the time would slow down or will become faster, depending on whether the observer is traveling at a very high speed or observer is in influence of some massive object. And this the traveling at a high speed, resulting in slowing down the time can nicely be calculated or understood with the twins paradox. And at the same time, as I said, I'll talk about this interstellar movie. This was a very popular meme in those days when the movie came out. This is the scene again from interstellar movie, and it says that 1 hour on this planet is 7 years on Earth. And this guy says that, great, I'll do the PhD here. I can finish it in 1 hour of Earth, like 1 hour here and 7 years on Earth. So 7 years of work can be completed in 1 hour, which is a misplaced concept, anyways. But this is a scene from movie Interstellar, and if you remember the movie or if you've seen the movie, this planet which they're talking about is very close to a very massive black hole. So it is the gravity is very strong there, and hence the time is very slow. Right. And I forgot the name of this planet, probably Miller's planet or something, but in the movie. But yeah, it's basically because it's very close to the black hole, the time slows down there, and they suffer the consequences on that planet. Great. So, these are some very interesting things, but they sound very irrelevant, right? How does it matter that time slows down when you reach the velocity of light? Who's going to travel at the velocity of light or even closer to that? Or where do we see it or feel it? In movies? Yeah, in movies we can do. But, and this movie, I am specifically mentioning this movie is because this movie was just like Nolan's other movies is made with a lot of detailing of science and some exact calculations. So I will talk about it again at the end of the presentation, how it was, made as perfect as possible from the science perspective. So these things sound very irrelevant, like, time slowing down with the high speed or time slowing down when you are close to some black holes or something. We are not going to go close to the black holes in our lifetimes, or at least our few generations of lifetimes. And we are also not going to travel at the speed of light, at least for a few decades at least. So these things are not really relevant. We perceive that these things are not really relevant, or why should we study this, and how does the Einstein's relativity matter? Also, how do we verify it? Like, Einstein says that light bends if it is under the influence of a very massive object because of the gravity curving the space-time. But is there a way to verify it? And anyway, these are not of use to me, so I wouldn't concern about it. These are some concepts that I have had in my mind before I learned this concept in more details, after MSc. Yes, we can we can experimentally verify the fact that light bends. And this was first observed by Sir Arthur Eddington in 1919. This was this famous solar eclipse. And the idea is that, during daylight, we cannot see the stars, and we do not have any object which is very heavy, very massive that can bend the light around us. The closest object which is massive enough to bend the light is the sun. So if at all something can bend the light in nearby region or something that we can experience or measure, the light has to bend by the sun or near to sun. So the idea, Sir Arthur Eddington proposed this idea that, in 1919 we're going to have this solar eclipse, and there are he had this star clusters behind it which are exactly mapped. So geometrically, the stars are going to be behind the sun, and I should not be able to see the star. But during the eclipse, when the light from the sun is completely blocked, and if the light bends, at least there will be one ray which would be traveling close to the sun and then would bend towards me, because the light from that star is being emitted in all 360 degrees. There would be at least some rays which are traveling exactly in the direction close to the sun and then bending towards me, so towards Earth or me or observers. So if that happens, we should be able to see these stars during the eclipse, despite of the fact that physically they are behind the sun and we should not be able to see. So they did this experiment in 1919 at 3 different places, I guess 2 or 3 different places. One of them being in Latin America, on the mountains. And so they had the teams traveling in different areas, and they all, tried to measure, like see and record the stars exactly at the same time during the solar eclipse. And bingo, they saw it, right? So that was the first experimental evidence or observation evidence of the fact that light bends when it travels very close to some massive objects. And now this theory of relativity, both the special and general theory of relativity, started making sense to more and more people. Earlier, it was acceptable only to a very specific fraction of the scientific community. But after this experimental validation, the special and the general theory of relativity started getting more recognition. Because also Sir Arthur Eddington had that reputation of a great scientist, so that carried the weight. And we now know that the light actually bends. All right. So with that validation, we get to know that fine, it is real. All right, like general theory of relativity works, although it's against our general perception or intuition. It is counterintuitive, but it works. The light bends in vacuum without interacting with anything, just because of the bending of the space-time, and time dilation takes place. Probably we have not yet talked about the experimental evidence of time dilation, but there had been a lot of time dilation evidence by that time. One of the popular one being which detected much later, is the detection of muon, right? Because theoretically muon should not be able to we should not be able to detect the muons because of their very fast decay time, but because of the time dilation, because they travel very fast, they do get detected. And then there are other things. So now we can exactly calculate the time dilation, and we come to the question that even if it is real, how is it helpful to me? How is it useful to me? So again, like for my young friends in MSc, I'll just quote this example. I'll just use this example that we know that the satellites travel very fast now. We have lots of satellites in the orbit of the Earth, and they are traveling at a reasonable, not of the order of the velocity of light, but they are traveling with reasonably high velocities. And if they travel with reasonably high velocities, the clock and clock on the satellite should tick slower than the clock on the Earth, right? So this was the idea that if satellite is traveling at certain speed, certain velocity around the Earth in the orbit, we can exactly calculate the slowing down of the clock on contradicting events. The satellite clocks should move slower because they are traveling at a very high speed, but then they should move faster because they are under lesser influence of Earth's gravity. And both these things happen. The general theory of relativity causes, I should not say it causes, but it explains that for the satellite clocks moves faster by 45 microseconds because of lesser influence of gravity. And at the same time, the special theory of relativity predicts that the clock on the satellite would move slower by 7 microseconds per day than the Earth's clock. This is per day. So every day, the clock on the satellite would be ahead by 45 microseconds because of lesser gravity, but lagging by 7 microseconds because of the higher speed. And so effectively, we need to correct the satellite's clock every day by 38 microseconds, and that's a good amount of correction. So the reason when we started using GPS, our accuracy was not so good is because these corrections were not accurate. And now, as we are making this correction more and more accurate, our accuracy of the navigation, GPS navigation, is increasing. And with this correction, thanks to Albert Einstein, thanks to theory of relativity, which we thought is just a theoretical concept which we can never use. Now we are using this concept, using these ideas to correct our clocks in the satellites, in the GPS satellites, and that helps us navigate very accurately. And now we are running multi-million-dollar businesses on the navigation technologies. So we've got GPS, we've got all GPS navigation based weapons and Zomato delivery system. We can track our order on the Zomato because we know exactly where this guy is bringing my food. And so the things that now we are using a concept proposed by Albert Einstein purely as a scientific curiosity into our day-to-day life and making the $1 million business around it is the fact that every scientific curiosity-based ideas may result in some great technology. So although the ideas may start from curiosity, may start from just some accident, eventually it can become a very interesting and very important technology in our day-to-day life. And this is one of the best examples to explain it. Apart from this time dilation, one more very fascinating outcome or prediction of Einstein's general theory of relativity was gravitational waves. And it comes from the fact that space-time is a common entity, and entire universe is in this wrap of space-time. So the idea is that this gravity needs to obey the principle of relativity. And remember, as I said, the c is not just the speed of light. C is a limit that defines the maximum speed anything can achieve, and gravity being one of them. So even the gravity cannot travel faster than the speed of light. So the effects of gravity, if something happens, the effect of the change in the mass or change in the gravity's influence would also travel not faster than the speed of light. And so but the idea is that it must ripple through the space-time to be able to reach to the surrounding. So what about the gravity from rapidly moving stars? Their gravitational effects at large distances can change instantaneously, right? They should also ripple through this space-time web, and that can be explained by the gravitational waves. And as I say, we generally perceive that the gravitational waves are outcome of the general theory of relativity, and Einstein was the guy who proposed it. That's not exactly correct, because in 1893, Heaviside first proposed this idea of the gravitational waves, and his idea was very simple. He said that just like the gravitation is following inverse square law, just like electrostatic forces, the electrostatic forces ripple through the space in form of light, then this gravity should also ripple through the space in form of some wave, and that can be called gravitational wave. Also, he probably did not coin that term. The idea was that just like light, the gravity should also propagate through the medium in form of wave. And then Poincare again proposed the idea of the wave, gravity moving in form of wave, and that was based on the Lorentz transformation. But it got popular by Einstein's predictions through general relativity in 1916, and he proposed that the gravitational wave must propagate with the speed of light. So he put that limit on the speed of light, and he said that there are three types of gravitational waves. One is transverse longitudinal, one is longitudinal, and third one is transverse. So he came up with the clearer picture of the gravitational wave, how it should look like, and how would it travel through the space-time wrap using his general theory of relativity. So now we have had a picture of the gravitational wave traveling in a transverse way or in a longitudinal way, or the combination of two as proposed by Albert Einstein. But this explanation was very counterintuitive, again, because it is a vacuum, and the imagination of this space-time wrap as a medium itself was not very clear or not very intuitive. It was very difficult for people to accept the idea of the gravitational wave traveling through nothing by means of a transverse or longitudinal way. And that included Einstein as well. Even Einstein was not sure whether the gravitational wave should exist and should move the way he is describing. He was kind of skeptical about it, and he remained skeptical for quite a long time. After 1916, when he proposed it, he was kind of working on it for next 7-8 years, and eventually in 1922, again Arthur Eddington came to the rescue and said that these three types of waves which Albert Einstein is proposing do not make sense, right? And I like this beauty of science. One point that I want to make today for my young audience, the MSc audience, is that science is beautiful if it is countered logically. There is no ego, there's no one who has an authority to say anything. Even someone as reputed as Albert Einstein was ridiculed very politely, and there'll be a couple of cases that we will discuss. So one of them being this, when Arthur Eddington said that the three types of the waves, the gravitational waves which Einstein has predicted, two of them don't make sense. Two of them are actually just artifact, and they come from the wrong mathematics done by Einstein because of the incorrect selection of coordinate system. So the two don't make sense. The third one, I'm not sure whether it makes sense or not, but probably it doesn't as well. Like that's what Eddington said, that even the third one, although mathematically I haven't proved it to be implausible or incorrect, even the third one is not making sense to me, but the two don't make sense for sure. Am I online? Let me check.
Yes, carry on.
Okay, thank you. So yeah, Einstein was kind of taken aback by this, but he wasn't very upset, because he himself knew that probably his theory is not making sense, and the description of the gravitational wave should not behave the way he's describing in his paper. Einstein, being Einstein, took about 14 more years to kind of work on that theory. After 22, he came up in 1936, and by that time he moved to US. So in 1936, he was in US, in America. He fled from Germany because of the uprising of those fascist regime, and he was then residing in US, and that was a completely new system. And then there he was working with Rosen, and these two guys, Rosen and Einstein, submitted a paper to Physical Review, which was a well-established American journal in those days. And they claimed that gravitational wave cannot exist. Remember, Einstein, who predicted the gravitational wave based on the theory of, general theory of relativity, is now, after 20 years, in 1915 or 1916, he predicted the existence of gravitational wave based on his general theory of relativity. After 20 years, in 1936, he is saying that gravitational waves cannot exist. I was wrong. 20 years ago when I said that gravitational waves can exist. It cannot. And interestingly, that paper went for peer review to Robertson. Robertson was a very popular, well-known scientist in those days. And the paper went to Robertson, who, just like the current days of peer review system, read through the paper, did the double check on calculations, and returned the paper, rejecting it, and saying that he sent a comment that said that the conclusion is incorrect. I don't believe that the gravitational waves cannot exist. Right? Einstein was right when he said gravitational waves do exist, and is now wrong after 20 years when he says that gravitational waves cannot exist. And then the paper went back to Einstein with his comments, and guess what? Einstein was furious. He wasn't furious because of the comment, but he was furious because he wasn't aware of this peer review system at all. He did not know that the papers can be sent to a third person without the consent of the author, and can be read by a third person before it gets published. So he was very angry on the journal. He wrote to the Physical Review and said that I'm not going to publish anything ever in your journal now. You shouldn't have sent the paper for review like this. I mean, who's someone to read my paper and comment? He can comment after I publish, but cannot comment before I publish. So he withdrew the paper. He did not respond to the comment. He withdrew the paper and said that I'm not going to publish anything in Physical Review now. PhysRef is done now. But then, his assistant, this Leopold Infeld, who was also in contact, he knew, Leopold Infeld knew Robertson personally, and then he might have some conversation with him, and eventually, understood the problem. And Infeld convinced Einstein that the comment is correct. The gravitational waves can exist. Our mathematics is wrong, and we are wrong in, So basically, the mathematics was about a solution of field equation which resulted in singularity. And this guy Robertson said that the singularity which you are achieving, that concludes that the gravitational waves cannot exist, is because of, again, wrong coordinate systems you are using. So, it's just the mathematical jugglery which is giving you the wrong conclusion. And if you correct that, you will arrive at a feasible solution of the field equation resulting in gravitational waves. So Einstein again reworked on the problem. Of course, he got angry. He withdrew his paper, but he did not give up on the idea. He started working on it. And this time, he concluded that gravitational wave is possible. He published it, not in Physical Review this time, but in some other journal. So ultimately, Einstein first proposed the gravitational waves through his general theory of relativity. Then after 20 years said that, no, I was wrong. Gravitational waves cannot exist in nature. And again, after about 6 years or so, he published a paper which said that the gravitational waves do make sense. Cool. And then, once it was established, and then there were a lot of other people working in the area who proved that actually gravitational waves make sense and they exist. So now, the question was different. Now that we had a kind of a consensus of this on the fact that gravitational waves can exist. Now everybody was working on a different question. The question was that, does it have any physical significance? Even if there's a gravitational wave, how does it matter? Can it transmit energy? Can it do work? Because the waves are of physical significance only if they carry the information or if they do some work. So that was there's a very famous argument given by Feynman. Known as the sticky bit argument, and it proposes that the gravitational waves actually do work and has the energy along with it. It carries the energy along with it, and it was later proved by Dirac as well. He theoretically proved that the gravitational waves can have a well-defined energy density. He did it in 1964. By that time, Einstein was not there with us anymore. All right. So once Dirac approved the idea of physical significance of the gravitational waves, a lot of people started working on detection of the gravitational waves. If there's an energy carried with the wave, if they exist, we should be able to detect them, right? And so a lot of people started working on it, but some of the known names were like Weber. James Weber started working on it with a different idea. He made this Weber bar, which is basically an aluminum cylinder. So it's like, this is an aluminum cylinder, a big, very massive aluminum cylinder with some piezoelectric sensor on it. And it has a very fixed resonance frequency. And if there's a gravitational wave interacting with it, the frequency would slightly change because the dimension would slightly change. The idea is, if the gravitational wave exists and if it passes by me or if it passes by the Earth, the wave is basically traveling in the space-time. And so it should distort the space-time. When it passes, just like a ripple passing through the medium, it should change the medium and it should create some distortion in the medium. So if there's a space-time acting as a medium, the gravitational wave should kind of, move the space-time, which means the entire space should either contract or expand. And if that happens, this aluminum cylinder should also change its dimension. And if it changes its dimension, the resonant frequency would change. And the Weber said he would be able to detect this change in the resonant frequency by measuring it through the piezoelectric sensors. So with that idea, he started kind of detecting it. And bingo, in 1969, he detected the first gravitational wave. He reported it. He said that I have detected the first gravitational wave using my Weber bar. It wasn't called Weber bar then. It was known as Weber bar later. But he said that using this aluminum cylinder, I could detect this gravitational wave. And in 1970, he detected several, a series of various events that produced the gravitational waves. And all of them were pointing to the galactic center, the center of our galaxy. And he said that the center of galaxy is a big source of this gravitational waves, and we are detecting it quite often, very regularly. So the Weber bar became popular, and again, one of the beauties of science, once, no matter how big scientist you are, once you report something which is too good to believe or which is very exciting and interesting, a lot of people would start reproducing it. And so a lot of other scientists started reproducing the result of Weber, and none of them succeeded. Not a single successful result was obtained except the results reported by Weber. So eventually it was proven and accepted that the signals which were recorded by Weber were just spurious signals and not actually the gravitational waves. So that first detection of gravitational waves in 1969 turned out to be the false positive. All right. In the same period, Hulse and Taylor published a very interesting, very important paper when they did not experimentally detect the gravitational waves, but they calculated, they modeled, binary pulsars, and these binary pulsars were decaying in their orbits, merging slowly, and their decay process would exactly match with the emission of energy in form of gravitational wave if GR, general theory of relativity, is used. So in 1974, they kind of reported these calculations and said that probably that first observation of merging binary pulsar is creating this gravitational waves, and they can be exactly calculated because they are matching with the GR model. And they got Nobel Prize in 1993, about 20 years later, when that was established and confirmed by various other experiments and calculations. Great. So in 1974, we had the first indirect observation of gravitational waves by this Taylor's paper, but we are interested in seeing it directly, right? We want to feel the gravitational wave directly. So how do we proceed? And the answer is light, the most fascinating object as proposed by Einstein. And let us pursue the light. Idea is very simple. Michelson Morley did this experiment. They made this interferometer, and this is a very common apparatus found in almost all UG and PG lab around the world. Probably university laboratories would also have this. This is known as Michelson interferometer, and they did this experiment to confirm the presence of a medium called ether. And they did not succeed. It was a null experiment. Like, it did not result in the existence of or proving the existence of ether, but it proved that there is no evidence of such medium. But anyways, that this experiment became important later. So what is the experiment? The experiment is very simple. You have a light beam which is coherent beam, so laser is the most appropriate source, and have a laser beam going in one direction. Put a beam splitter on the path, split the beam into two parts, so now both of them are coherent, and let them travel in two perpendicular directions. Put two mirrors at two ends and let them reflect back and come back to the beam splitter, and let them interfere. Since both of them are coherent, the sources are coherent, they would interfere almost perfectly. And depending on the path difference between them, because they are traveling and traversing two different perpendicular paths, depending on the path difference between them, they would either interfere constructively or destructively and create a pattern on the screen. So basically a very simple MSc experiment or BSc experiment that have a laser beam split it into two perpendicular beams would then reflect from two mirrors and come back and meet and interfere, and depending on the path difference, they would either create a dark pattern at the center or the light pattern, or basically you will have a dark patch or a light patch, bright patch. You call it an interference pattern. Great. Now, if the gravitational wave is traveling and passing through the interferometer, this interferometer in space, as I said, when the gravitational wave passes, the entire space-time distorts, which means the space in one direction may get contracted and the space in the other direction may get expanded, and then vice versa. You will have a distortion of space-time. So that means even without doing anything, if you have this Michelson interferometer, have two arms perpendicular to each other, and when the gravitational wave passes by, it will contract one of the arm, not the other one. And since light travels at that constant speed, irrespective of any distortion from space-time, what will happen is the one that is getting contracted has a lesser length because of this distortion. The light will travel fast. Will arrive at the beam splitter quickly as compared to the other beam, and that would change the path difference, right? That would change the optical path difference between the two. So this interference pattern will get distorted, right? So if you have a bright pattern, it will change slightly. If you have dark pattern, it will change slightly. And the idea is that let these two beams split into perpendicular directions, get reflected back from the mirror in the Michelson interferometer, come back and interfere destructively, so that there's a dark and your photodetector is not seeing any light. Now if the gravitational wave passes by, it would contract one of the arm and expand the other one, creating an optical path difference, and that will change this condition for the destructive interference, and the destructive interference will become less prominent and some light will appear on the detector. So if you see some light on the detector without doing anything, just by contraction of space, then probably gravitational wave has passed by, right? So this is the idea, very simple. And a lot of people started working on this idea all the way from 1960s. So in 1967, the Weiss, who is the key person throughout this history from MIT, initiated the construction of the first prototype of this interferometer for the detection of gravitational wave. And he got the funding from military. But eventually it was not successful. He had to terminate the project in the midway, could not complete the construction of the Michelson interferometer. In 1968, Kip Thorne at Caltech again started theoretical calculations on using the Michelson interferometer for the detection of the gravitational wave, and he kind of modeled it and calculated the required amount of length and what would be the required strength of the contraction to be able to detect it by this technique. And he was convinced that with this idea of Michelson interferometer, we should be able to detect the gravitational wave if it passes by on the Earth. So theoretically, he kind of established the fact that this idea will work. And then a lot of small prototype systems were built from 1960s and 1970s, but they were all at laboratory scale, like few meters of length of Michelson interferometer, and none of them was successful in detecting the gravitational waves. The problem was in the scale, right? Because they were all laboratory scales, like the distance that light had to travel was very small, and the effect of gravitational wave is so feeble that the change in the length of arm is almost insignificant, almost negligible, right? There's no change in the there's no measurable change in the space in one arm that a Michelson interferometer of the laboratory scale could detect. So what can we do? We can increase the length of the arm, right? I mean, I have a Michelson interferometer in our lab, but the arm length is about 10 centimeter or 15 centimeter. In those days, they were trying with a few meters, but the idea is that if at all we want to detect the contraction of space or expansion of space, which is like 10 to the power minus 21 order of magnitude different from the length of the arm, then you have to increase the length of the arm. Like you increase the length of the arm so that that fraction 10 to the power minus 21 still becomes significant enough to be measurable. Like we can measure it. So the idea is like increase the scale, the length of the arm. So that requires more money, and people started writing the project. And eventually, in 1980s, in 1980, the NSF funded this study of a large interferometer. And I'm saying that NSF funded the study, not the actual experiment, just the feasibility that is it possible to make a big interferometer that can detect the gravitational waves. Again, that project was led by Weiss. And in 1981, this Caltech constructed a 40-meter prototype. So, they came up with the actual Michelson interferometer, which had 40-meter length arm in one direction and 40 in the other. And then this Drever, Thorne, and Weiss formed a LIGO committee. So they said, like, okay, let's make a bigger interferometer so that we should be able to detect the gravitational waves. And they made this committee and started writing the proposal to the NSF. For now actual construction of the project, this LIGO project. And guess what? The proposal was turned down in 1984, and again they wrote a new proposal in 1985. It got turned down. So when I read this, or when I write this like when I made this PPT, I felt good about my project proposal getting turned down by DST sometimes. So yeah. This committee then a couple of times wrote the proposal but did not get the funding, and eventually the committee got dislodged, and a professor from Caltech got appointed as a director for this project now, and he led this project and got the funding in 1988 eventually. Again, like the project was running at a very slow speed, at a speed of sloth, and from 1989 to 94, LIGO did not get a proper funding. Like their review was not good. The comments during the review said that the progress is not satisfactory, and we are not going to funding it anymore because there are other priority projects. So they did not, although they got the approval, they did not get the fund from 89 to 91. In 1992, they got $23 million grant, but again got frozen. They said like, no, the progress is not poor and you cannot use this money. So there was a lot of trouble in getting this funding because this was a basic science project, right? Detecting gravitational wave is not going to help any country making weapons. So there's no direct immediate implementation, and so they said that for a basic science project we cannot spend so much money, and the funding was turned down again and again. Finally, Barry Barris got to lead this project. He was appointed the laboratory director, and the NSF, the National Science Foundation, gave the last chance that all right, we are funding to you once, and you produce some result or forget about the funding for you. So this time they came up with more sound proposal. And remember, all this, like, from 1980s to 1994, it was only about the design of the interferometer and the money. Like, it wasn't about the actual construction. It was only about the design part, which was getting rejected again and again. And finally, with finally in 1994, with Barry's leadership, they got this $395 million of project for the LIGO, and they started the construction in 1994 and 95. In 1994, they started in Livingston in Louisiana, and in Hanford in Washington, and 1995 they started in Louisiana. And these two laboratories are very important. We will come back to this later also when we will talk about the India's component. All right. So initial construction completed in 1997, 98, and the detectors were then installed by 2002. So they started taking the data of gravitational wave measurements from 2002. And as I said, the size was the key, and also the reason for my involvement or my excitement about these things. Right, I'm not a person working on LIGO. My PhD was on lasers, but I have never worked on LIGO project. But since my PhD was on lasers, I was attending a conference where one of the authors it was an international conference, and one of the authors from LIGO collaboration presented a paper and showed the picture of this newly constructed Livingston laboratory in those days. And the size, the scale at which they developed kind of, grabbed my attention. And I started reading about it more and more. And this is the size, guys. Like, it was a thought experiment started by Albert Einstein. And eventually in 1994, we had these two laboratories trying to detect gravitational waves, which are outcome of the general theory of relativity. And look at the size. Like, these are 4 kilometers of arms stretched in both directions perpendicularly. So 4 kilometers in this side and 4 kilometers perpendicular to it at two different locations. One is in Washington, which is in northwest of US, and the other one is in Louisiana, which is in the southern part of the US, about 3,030 kilometers apart from each other. It's like, that's also very interesting. It's like the distance between the Louisiana and Hanford is 3,002 kilometers in a straight line, but because of the Earth's curvature, it turns out to be 3,030 kilometers. And also, they had to limit this length of 4 kilometers because of Earth's curvature. Because then, if you, like, beyond 4 kilometers, to keep it straight, they had to build a really big towers to make that, take this Earth's curvature into consideration. So yeah, these are the 4 kilometer long arms. This is Hanford Observatory, and this is Livingston Observatory in Louisiana. The antenna of the LIGO observatory extends over 4 kilometers, as I said, about 2.5 miles in each direction. And this is how it looks like from the top. All right. And the beauty of this project and this entire concept is that, it started with a very basic science problem. The detection of it required a lot of technology, and eventually it became a technological challenge. So LIGO has been a technological wonder, and there are lots of challenges which they solved one by one slowly, and kept on improving the technology. So from 1994, when they started making it up to the 2002, when they installed the detectors, and then continuously upgrading the detectors to improve their accuracy of measurements, this LIGO has become a technological wonder. And look at the challenges. Like, okay, this is just to get the idea of size. Like, look at the size of this arm with respect to the car moving around it. So the challenges are enormous. Like, imagine, like, those, as like Bala sir was presenting the talk earlier, he was talking about this plasma and material synthesis. And we also do the material synthesis here, and we do it in vacuum chamber. And this vacuum chamber are kind of a maximum like 2 feet, like maximum 30 centimeters or 60 centimeters in height or diameter. And these chambers require, like the one that I work with, requires about 10 to the power minus 6 torr of vacuum, right? And that too is a big deal, like hell of a job to maintain 10 to the power minus 6 vacuum in just a couple of feet big chamber. And now we're talking about the chamber, which is 4 kilometers long and almost 1 meter in diameter. And imagine maintaining 10 to the power minus 9 torr vacuum in that 4 kilometer long arm. It's a very big challenge from the vacuum science perspective. And then they have these chambers which are evacuated one by one to get the high vacuum. And also then they have to take care of the water vapor, like remove everything which is in the memory of the chambers. And the vacuum, maintaining vacuum is one of the biggest challenges. Another challenge is this Okay, another challenge is the seismic isolations. These are some specifications. The laser they are using is 10-watt laser, which is then multiplied by the multiple reflection to get about 200 watt of power. It is NDR laser, 1064 nanometer, and then there are some very sensitive optics to kind of reflect this laser perfectly for multiple times. This optics is suspended by single steel wire to get that pendulum benefit. So the pendulum kind of prevents it from many vibrations around it. And then this optics are also installed on this vibration free tables, and this vibration free tables kind of suppresses all the surrounding vibrations. They say that even a truck passes about a kilometer away from it can detect, like they have this active vibration cancellation mechanism which will kind of cancel the vibration because of a truck traveling 1 kilometer away from the sensors. And then this pendulum again further improves the accuracy and suppresses the vibrations. Also, they have to kind of take care of the seismic activities, like the vibrations from the Earth's crust, and so they have installed this all the seismic sensors, and any minute vibrations they would just not consider the data during that time when there were seismic activities reported. So this is like a challenge to get rid of these vibrations because of some physical mechanical movements around it, as well as some movements of the seismic activities. And it is done by two different technologies. One is the active vibration cancellations. Now, like in early 2000, this was a very interesting technology and very new technology. Now, as a byproduct of this works here as well as in NASA, now these technologies are coming to the day-to-day life as well. Nowadays, like even the cameras that we use, the high-end cameras that we use, have this active vibration cancellations mechanism built into it. But in those days, in early 2000, this active vibration cancellations and the passive cancellations of vibrations were a great deal of work. And then eventually, it became a bigger and bigger project because of inclusion of multiple institutions like Max Planck, Caltech, and the institutions from Italy and Germany, and a lot of institutions then collaborated with the LIGO. So LIGO has two major components. One is the LIGO lab, which is kind of doing the experiment, and another one is LSC, which is LIGO Science Collaboration, which collaborates with other institutions and kind of does the organizational work. So detection followed by astronomy is done there. Science collaboration is done there, and the funding is still from the NSF mainly. These are the two locations of this LIGO labs, which are detecting the gravitational waves using laser, using light, which was outcome of the gravitational, like general theory of relativity, the gravitational waves basically. All right. Apart from US, in Europe, there was this Virgo lab, which was also active all the way from early 2000 and was collaborating with the LIGO. This is just outside Pisa in Italy. And there's another one, GEO 600, which is a small, I think 1 kilometer, 3 kilometer arm length, small interferometer. And all three are working in tandem. Vigo then, Virgo is in Italy, just near Pisa. It is also 3 kilometer interferometer. And then there is a big network. One is Germany, one is in Italy, two in US, and one in Japan. So these 5 interferometers are now in process of detecting the gravitational waves. And finally it happened in 2015. On 14 September 2015, when actually they were testing it. It wasn't even running, like the detector was not even in running mode. They were just testing it, and they detected this chirp signal. As I said, the signal is these 2 laser beams are going in perpendicular direction, getting reflected back from the mirror 4 kilometers apart, and then creating an interference pattern with destructive interference. So there's a dark on the photo detector. The moment space gets contracted because of the gravitational wave, there will be a bright pulse on the detector, and this bright pulse would create a pattern of wave which would kind of reflect the pattern of the gravitational waves at the frequency at which it is traveling. The gravitational wave can have frequency very low, less than a hertz to a few kilohertz. I mean, it falls in the audible range, and so when they kind of converted into audible signal, that chirp signal, it sounds like the bird's chirp, and so they call it chirp signals, chirp, CHIRP. Right. So it was it was not even in taking the data, it was just being tested, and they detected this signal in 2015. Remember, they did not detect any signal from 2002 to 2010 for 8 years. Then they updated the detector in 2014, and finally, in that first run after updation, they got the first signal. And they detected the signal. In 2015, they announced the result, and finally in 2017, they got the Nobel Prize for this discovery. These three guys. Barish, Thorne, and Weiss, who all three were involved in the LEGO project from very beginning, all the way from prototype or conceptualization of idea to the final detection. And I said, Interstellar, the Skip Thorne was one of the advisors to Nolan in making of Interstellar. So he helped with all the, scientific scenes, like the scenes which involve some scientific details. All right. Why am I taking this topic today? Because as I said, and as the theme of the program is, we are moving towards Vikshit Bharat. And we are not anymore a developing country. We are working hand in hand with the developed countries, whether it is technology development or the scientific ideas. And the fact that now we are in part of this, we are one of the collaborators with the LEGO project, along with US and European and Japanese partners. The LEGO India is now an official partner of it, and we are building this sixth. Apart from this 5, we are building the sixth LEGO experiment. It's called Indigo, Indian Initiative for Gravitational Wave Detection, and this is now being built in Maharashtra. The beautiful part is that this project was originally, the US wanted Australia to be part of this project. So it was originally planned in Western Australian desert, and the condition was that the US will provide all the technological training and some components for detectors to establish this project, but the land, manpower, and other funding should come from the host country. And Australia somehow did not take that offer and was not ready to fund that money for this peripheral task, and Indian government did it. Like India said that we're going to take it and we will do it. And just after the announcement of the first discovery, within a week, our Prime Minister announced that we are official partner with this LEGO, and we will be building a LEGO project in India, in Maharashtra. So the observatory originally was getting 13 billion rupees, 13.5 billion rupees fund from the DST and DAE along with NSF US. So original plan was 13 billion rupees, but then Indian government increased the budget, and in 2023, just last year, in July, they approved the budget of 26 billion rupees, which is about $360 million, and that budget is sanctioned. It is already work has already started in Hingoli district of Maharashtra, and this is LEGO India website where work is being done. DAE, DST, and NSF are the major funding agencies, and they are collaborating. They have done the MOU, and these are some areas where LEGO India will be useful. Like they are working on the basic physics part. They are also working on the precision measurement technologies development, and they are working on the quantum technology development as well, along with the laser science. So a lot of peripheral development would take place along with the gravitational wave observations, and of course higher education and outreach would be one of the major components of this project. So India is now hand in hand with the Viksit developed countries when it comes to basic science and technology, and that's so amazing and proud feeling for all us scientific communities in the country. All right, so what next? I'll just quickly finish this slide in 5 minutes and come to the end of the talk. So we are not ending, like the V means humanity is not ending at this point. Even 4 kilometers is not sufficient, although we have detected more than 70 events so far after the first detection through these 5 detectors. And also few events had the follow-up of microwave and gamma ray burst detection as well. So the LEGO detected a gravitational wave, and from the same direction, the gamma rays burst was detected by some satellite observatories, and so that confirmed a big, massive event in the space that generated a gravitational wave, and also the gamma ray burst from the same source. So we don't want to stop at 4 kilometers. How do we extend the length of the arm? Well, we can go extraterrestrial. We can put the satellites and then align the satellites to make the 90-degree microsensor interferometer, and then there is no limit. Like we can have a 5 million kilometer long arms, and the detection would be much more accurate than what we are doing now. Also, this is a very far end project now. There is no actual experimental work going on in this direction, but it's a very interesting project. All right, I'll quickly in next 3 or 4 minutes, cover this another idea where light has been helping us with a very amazing technological, adventure, and that adventure is interstellar explorations. So I'll, like Einstein chased the light in his thought experiment. He just thought about it. But can we actually ride the light? Like, can we actually go along with the light and travel and use the light as our thruster? So if we can do that, we can think of interstellar travels and find out a planet which is habitable in some other solar system. Because otherwise, there's no way. If you want to go, if we want to leave this solar system and take the humanity to some other place, we have to travel at the speed of light, or at least close to it. So this concept is again very old. Kepler started with this and said that the Halley's comet has always its tail away, like moving away from the sun. And then he wrote it to Galileo, and later Maxwell established that the light has the radiation and momentum. And so now by the 1880s or 1870s, it was known that light can exert pressure because it has momentum. The photons have momentum. And this idea was exploited by a lot of science fiction writers like Jules Verne. He said that someday we should be able to travel on the back of the light and reach to some other planets. And then Bernal, who also wrote some fiction, said that a form of space sailing might be developed which used the repulsive effect of sun's rays instead of wind. So the idea is like we use the radiation pressure as a wind and sail through it, just like a ship sails on the sea using the wind. So a space vessel can be designed with the large metallic wings, and using the wind pressure, just like the radiation wind pressure, we can sail through the space. And so he proposed this idea to go to the Neptune and then come back and take the sun's round and go to the another solar system. Arthur Clarke, again a fantasy writer, science fantasy writer, came up with this idea that solar or like light yacht, the yacht which would use the solar sails to do a race. And Carl Sagan, again like a great scientist and a great writer, came up with this idea of light sailing or solar sailing. But it all looks like the sci-fi stories, right? It's all science fiction. How close we are to the reality? Well, the first formal technology design efforts were started by the JPL in 1976, way back in 1976. In 2005, the Planetary Society is a organization that attempted to send a solar sail satellite named Cosmos 1 into space. And the idea was to see whether it can be controlled using the radiation pressure or not. But it failed. It did not reach the orbit, and they could not install it in orbit successfully. Then in 2010, this NanoSail D2 was a small satellite that was built by NASA's Marshall Space Flight Center, and it was like just a small cube of 30 by 10 by 10 centimeter with 4 kilogram mass, and it was to be launched in space for testing of deployment of sails. Basically, the problem is that this sails, the wings, should be very large because the pressure density is not very high. The momentum, the light pressure density is not very high. So to exploit that pressure, we have to have a very big wings, big sails. To deploy this space in the space is to deploy this sails in the space is challenging, and they wanted to test this. So they sent this NanoSail D2 in the space. They launched it into the orbit, but as I said, like science and technology is sometimes funny. So it was planned to be deployed from the FatSat satellite around 3 December 2010. 2 weeks after the launch, after putting it in orbit. The satellite did not eject at that time. That solar sail, that small cube satellite was supposed to be ejected out of the big satellite, and it did not get ejected. But after a few days on January 17th, like after about 47 days or 45 days or so, it got ejected automatically on its own and deployed even the sail 3 days later. So what it was supposed to do on 3rd December, it did on January 17 on its own. So it failed initially, but later on it triggered automatically and went into the orbit and deployed its solar sail. And then it started sending the beacon signals to the Earth station after January 19, 2011. So Again, like, Light Sail is a project. It has Light Sail 1 and Light Sail 2 projects. These are already tested in the space. Light Sail 1 has already been tested in the orbit. And finally, on May 2015, Light Sail 1 launched. It deployed its solar cell on 7 June 2015 and re-entered the Earth's atmosphere as planned on June 2015, during June 2015. And this was reported by none other than Stephen Hawking. It is also death anniversary of Stephen Hawking today. And I saw this post by Stephen Hawking on social media in 2016 when he said that we are launching another big probe that will test our technological readiness for solar sailing. And I posted it saying that this is insane. Like, we are reducing the gap between science fiction and the reality very quickly. And when someone like Stephen Hawking says it matters a lot. So, so excited about it. And finally it happened. In 2019, the Light Sail 2 launched the secondary payload on the space test program on Falcon Heavy rocket. And it deployed its solar sail on July 23 and successfully downlinked photographs of the deployed sail on July 24. And finally, they could raise the orbit just by using the radiation pressure on Light Sail Solar 2. So the intended objective of kind of controlling the altitude of this satellite by using the sun's radiation pressure was achieved in 2019. So with this, I would end. So we saw two important technological breakthroughs where light was our rescue or our guide. So with this, I would end my presentation and see where we are.
So thank you, Dr. Vipul Kheraj, for a very nice and interactive talk. I would ask the participants, if you have any questions, you can unmute yourself or you may write in the text box. Yes, there is one question from Chintan Panchasara that you can read.
Yes. So why is it important to make such observations at multiple places? There are two reasons. One, in science, we don't believe anything that happens once or at one place, right? We need the reproducibility, we need the repeatability. So just like, Weber reported the detection of gravitational waves way back in 1970, but when, others reproduced or tried to reproduce it, we realized that those were the false positive, right? The actual signals were not there. So of course, LIGO reported this in 2015, but we need other detectors to confirm this discovery. There were other claims which were later on rejected. There were lots of claims of gravitational wave detections by other other interferometry detectors as well. But some of them were true, some of them were not reproduced or not confirmed by the mathematical verification, so were rejected. Second and more important reason is, if you want to find out the source for it, one, even to start with, they came up with two detectors, not one. Because if you want to find out the source of it, we need to measure it at two different locations and find out the time gap between the two events. So if the gravitational wave travels, depending on in which direction they are coming from, they would either hit Louisiana first or Hanford first. So depending on which gets detected first or which detects it first, and how much time does it take to reach from one place to the other, we may exactly locate the source of it. That's how they are finding the source. And even for the first detection, they were very clear about the source of it. They were the two black holes merging with each other, and they exactly knew the location of that in the universe. So that identification and pinpointing of a location is possible if you have two different experimental laboratories and both of them detecting it at two different times. And then, from the angle and from the distance or time gap, we can calculate it. Having more number of detectors, it would be more accurate to find out the source. So that's one of the reasons.
Very nice. Anybody else, if you want to ask any question?
It is very similar to how, we need at least 3 GPS satellites in our field of view to be able to exactly locate ourselves.
Correct.
One satellite will not be able to tell us.
Yes. So I think there is no more question. So, on behalf of Department of Physics, Saurashtra University, Vigyan Gurjari, and GUJCOST, I thank Dr. Vipul Kheraj for giving a very interesting and interactive talk. It was really interesting on pursuit of light and enlightening exploration of the mysteries of universe. You started with the birthday of Einstein today. You recall us, explain why gravitational waves and how they are generated, how we can detect the gravitational waves, what is time dilation, uh, and what is the effect of time dilation in satellites and timings. Short story about idea of gravitational waves starting from Heaviside, Poincare, Eddington, Einstein, and so on. So many scientists. You gave very much brief idea about each work of everyone scientist. Sir Taylor, how to see gravitational wave directly using the light, Michelson-Morley experiment. Slowly you build the story of your talk, and finally you arrived at a LIGO experiment, and for the LIGO they got Nobel Prize in 2017. This was very nice talk, and
Thank you so
really
much.
appreciate. Thank you, and I thank you, the Department of Physics, Vigyan Gurjari and GUJCOST for giving me a chance to host this talk. So thank you, everyone. Thank you, participants. Without you, it is not possible to have a great talk. Two talks, really nice. Thank you.
Thank you, sir. Thank you so much.
Over to the coordinators.
Thank you, sir. Now I would like to invite Mr. Prem Mehta to deliver the vote of thanks.
Good evening, everyone. So, myself, Mehta Prem, Department of Physics, Saurashtra University, RAJKOT. It was a wonderful and amazing session of yours, sir. I can surely say that your today's talk has planted seeds of curiosity into young minds, which will lead many young minds towards research field. We all are so thankful that you had given your valuable time and knowledge to us. I wish to express my sincere appreciation to everyone who took part in this insightful talk. On behalf of Department of Physics, Saurashtra University, Vigyan Gurjari, Gujarat Prant Unit of Vigyan Bharati, VIBHA, and GUJCOST, Department of Science and Technology, DST, under Gujarat Vigyan Sammelan, I am deeply grateful to the distinguished speakers we have with us today, Dr. Balasubramanian C. and Dr. Vipul Kheraj. Your enlightening presentation truly inspired us, sir. We are so much thankful to you. I express my gratitude to our honored guests, Professor Utpalesh Joshi and Professor Bharat Kataria. I would like to thank you, our Chief Patron, Professor Nilambari Ben Dave, who provided us consistent support and encouragement for organizing these informative seminars. I would like to convey my gratitude to our patrons and co-patrons, Professor Chaitanya Joshi, Professor Girish Bhimani, Dr. Narottam Sahu, and Dr. R.G. Parmar. My sincere thanks to the conveners of GVS, Professor Nikesh Shah and Professor P.N. Joshi. I am very thankful to Professor Deepak H. Gadani for chairing this session very nicely. I am also much thankful to our event coordinators, Dr. Piyush Solanki and Dr. David Dhruv, for their constant support in this event. I am very much thankful to everyone present here, because without you, this event or this speech rather would be incomplete. We will meet again tomorrow at same time and same platform to fulfill our thirst of knowledge. Thank you.
Thank you, everyone.
Thank you, Vipul sir. Next one.
Thank you, sir. Thank you so much.